for the today's session. I welcome Professor Major Dr. Chaitanya Sangvi. Sir is Major. Sir is Professor in LD College of Engineering, Ahmedabad, Gujarat. Sir has completed his PhD in Earthquake Engineering from SVNIT, Surat. Sir has published a number of papers, technical papers in national conferences, international conferences, and various journals. Sir worked as a resource person in earthquake engineering. He has prepared 18 episodes on earthquake-resistant construction for civil engineering professionals with Education Multimedia Research Center, which was telecast on DD National Network. He has project on development of library of earthquake engineering in 18 colleges of Gujarat with Gujarat State Disaster Management Authority. He has also completed a project to develop the laboratory of earthquake engineering in the various colleges of Gujarat with collaboration with Gujarat State Disaster Management Authority. And this is a very unique project which is going on in India as well as in Gujarat State. He has coordinated various training programs in the field of earthquake engineering, and he has coordinated various training programs for the earthquake resistant design for professional engineers, architects, site engineers of various municipal corporations in the state of Gujarat, as well as in coordination with Gujarat State Disaster Management Authority. He has carried out various training programs on disaster management and mitigation for Class 1 and Class 2 officers of State Government of Gujarat at Sardar Patel Institute of Public Administration. He has also carried out a training program for earthquake-resistant design and durability-based design for executive engineers, deputy executive engineers, and assistant engineers of R&B department of Government of Gujarat. And he has also coordinated various training programs in collaboration with various IITs also. He is also carrying out various research and development programs such as develop learning resources on seismology, RCC, and machinery structures with the help of PDDC students, and also a very unique project which is to develop an earthquake engineering laboratory with the help of UG and PG students at LDC College, Ahmedabad, and which is has a national recognition also. He's also completed development for the shake table and various models used in the shake table testing with the Gujarat Council of Science and Technology, GUJC cost. He has also coordinated a unique national level model testing competition on the Terramar terror in earthquake engineering for various students of the engineering colleges. And most important part of sir is that he is very active in social services also, like he is working as an NSS program officers, and he has been awarded with the national award of best program officer of national service scheme by His Excellency President of India Shri Ramnath Kovind. He has also been awarded as the first Indian officer with the rank of major and became a Centurion blood donor. He's also been awarded the youngest Centurion blood donor by Indian Red Cross Society. And he has also received various awards like in year 2002, Shri Sundar Singh Bhandari by Honorable Governor of Gujarat. In year 2005, Pandit Naval Kishore Sharma. In 2007 by Shri Pankaj Udas, President of Maharashtra. And 2010, Chief Justice B.J. Diwan and Swami Dayanandan Ji. In 2011, by Dr. Kamala Ji, Honorable Governor of Gujarat, and also by Honorable Chief Minister Shri Narendra Modi. He has also worked as an officer in charge of various activities for the Gujarat Technical University as well as for the institute, and received award for outstanding work from Honorable Governor of Gujarat in year 2011. LD College of Engineering was awarded Outstanding Blood Donor Organized Award by Indian Red Cross Society and received the trophy for this. Sir is also very active in working as an NCC officer, and he has held a rank of major from 1998. And under his guidance, he is nearly training about 200 NCC cadets every year, and he has obtained the highest delta grading in all the trainings of NCC officer at national level. He has also coordinated the rescue and relief operation after the Bhuj earthquake 2001 by NCC cadets. Coordinated relief work for Gujarat flood victims, coordinated the relief work for drought in Saurashtra, and various other activities like blood donation, tree transplantation, AIDS awareness programs are carried out regularly under his guidance. He has also worked as an officer in charge for these activities for Gujarat Technical University as well as for the institute, and received the award for outstanding work from Srimati Kamlaji, Honorable Governor of Gujarat in year 2010. Additional responsibilities performed regularly under the university level as an officer of commissioner level and at the institute levels also. Sir is also a member of professional institute bodies like Earthquake Engineering Research Institute, USA, Indian Society of Technical Education, Gujarat Institute of Civil Engineers and Architects, Institute of Engineers India, Indian Geotechnical Society, National Program Center of Earthquake Engineering, Structural Engineering Forum of India, and also a member of Lions Club Maine. So on behalf of ATAL FDP program and University Institute of Technology, RGPV Bhopal, I welcome you, sir.
Thank you, ma'am. Thank you for very long introduction, and I think I'm audible, right?
Yes, sir, you're audible. And the peoples must know about your all like social activities also. So I have what we described it.
Right. Absolutely, because I think the society has given us a lot, and now it's a time to return to the society.
Yes, along with the technical, we must also give to the society also, and what you are doing.
Yes, absolutely.
Welcome, sir. So
yes.
we will start with the session.
Yeah. We will start the session. Thank you very much for the very long and nice introduction. And today's session is basically the earthquake laboratory session. Basically, we try to understand what is the importance of experiments in earthquake engineering. I can say that this session to be conducted in the laboratory. It's not online because I think if you have a feel of the laboratory, then definitely you will enjoy that how the experiments are performed in earthquake engineering. But I think COVID has made us to deliver such kind of sessions online also, right? So I'm presenting my screen, and if it is visible, please tell me. Is it visible?
Yes, sir. Yes, sir.
Right. Okay. So this today's our session. I'm very much thankful to Aruna Madam and the Rajiv Gandhi Pradyogiki Vidyalaya Bhopal for inviting me for the session, and I appreciate that such kind of effort is taken by the RGPV Bhopal, ATAL FDP on architecture design and construction practice. We have conducted this last year on the same topic at LD College. And, it's nice to hear that such kind of activities are going on in each and every part of the country. So today's my lecture will be on importance of experiments in earthquake engineering. If you have any question, please you can ask the question. I think we'll keep it at the end so that because when I'm presenting, I think I am not able to see you, right? So please, we'll continue with this, right? So we'll. I think that is it okay, ma'am?
Yes, sir. Very okay.
Yes.
If any questions are there, you can type in the chat box also. We will discuss it at the end of the session.
Right. Okay.
Yes,
Yeah.
sir.
Yes. So we'll start with the very fundamental things, and we talk about the disasters, and we know the various types of disasters we have: earthquake, we have a cyclone, we have a flood, the fire, we have landslide, liquefaction, we have tsunami, right? So as far as the disasters are concerned, many more disasters are there, and actually we have not named it, like chemical disaster, biological disaster, and many other disasters we are knowing. But I'm not writing here, I'm just writing few of them. But when disaster we are discussing, then generally we are categorizing this disasters, or we are classifying this disaster into either man-made or natural disasters, right? uh, I always saying that these are not the disasters, these are the hazards. These are the hazards, and these hazards will become disaster only when you are not prepared for these hazards, right? If you are prepared for the hazards, I think this hazard will not be converted into disaster, right? But let us discuss generally. In routine life, we are discussing that earthquake is a natural disaster. Cyclone is a natural disaster. Flood, when we are talking about flood, the flood may be natural or man-made, right? Or we can say fire, it is also natural or man-made. Why I'm saying this? You see, sometimes the flooding is taken place because of the excessive rain, and sometimes because of the human error. For example, if the dam will collapse, uh, then it is a man-made disaster because you have not adequately designed it, right? So the flood may be a natural, it may be man-made. Fire, it may be natural, it may be man-made. During the earthquake, if it catches the fire, but basically human error involves, and when the human error involves, you can say it is a man-made. Landslide again, the same thing, natural or man-made. Because some earthquake triggers, and when the landslide triggers in the hilly region, then it is a natural. But suppose if you are going for the mining, right, in the hilly region, and if landslide triggers, it is a man-made. Liquefaction, it is the side effect of the earthquake, and in case of a sandy soil, generally we are observing this liquefaction when it is not compacted and when water table is high. And the tsunami is generally, we say, it's a natural, right? Now you see, when we are saying earthquake is a natural disaster, then the certain question will be there. uh, uh, we are saying the natural disaster. Natural disaster means what? The natural disaster means nature is angry, right? Nature is angry. Now, simple example. If I'm saying a cyclone, if cyclone, during the cyclone, we are remain with we are not going out during the cyclone, right? We remain within our houses or our homes, right? So we are knowing that cyclone is a natural disaster, and we cannot approach the nature at that moment. So we are hiding ourselves in our houses, and once the cyclone is finished, definitely we'll come out, and we'll go to the nature, right? But in opposite to that, in earthquake, if earthquake comes, then what is happening? Earthquake, you are in the in your house, and suddenly if earthquake triggers, what you will do? You will come out of your houses, right? You are come out of the houses, and where you will go? You will select open spaces. Why open spaces? Because you feel safe there, right? And what is open space? The open space is nothing but it's a nature. So during earthquake, you are approaching nature. So we are saying earthquake is a natural disaster. If earthquake is a natural disaster, then you will not approach the nature during that particular time. Like a cyclone, during cyclone, you are not approaching, approaching the nature. You are not going out, right? But during earthquake, you are going out. What is the reason? The reason is we don't have faith in our buildings. We assume that our buildings are unsafe, and this building may collapse. right? And that's why we are coming out of the buildings, right? And we are approaching the nature. So therefore, I'm always saying that earthquake do not kill, but unsafe buildings do, right? uh, the main thing is that we have a fear that this uh, unsafe building will collapse and will die, right? And therefore these buildings are built by us. Therefore I'm always saying this earthquake is a man-made disaster, right? If I'm saying, if uh, I'm always saying earthquake is a natural hazard, but the disaster is man-made because we are constructing unsafe houses. That is the main thing. So I'm always saying the solution lies in the building, not in the earthquakes, right? Solution lies in the building. So we have to make safe houses. That is the most important part. Yeah, rather we are studying earthquakes and everything is pattern and everything. It is not that important. But under those earthquakes, our building should remain safe. And what should we do for that? And for that, we have to go for the good design. We have to go for the good construction practice, right? That is to be required. And a good healthy mindset that I want a earthquake safe society. That is what we want. And right then and then we build earthquake safe society. Otherwise it is very difficult. You see, if you look at the present scenario, the structure engineer is the most important person as far as the safety of the building is concerned, and he is the least paid person in the whole construction industry, right? This is what our feeling is. So actually the role of structure engineer is very important, and he or she should be paid handsomely, because he or she is providing the safety to the structure, right? That is important, right? So this is some basic thing I'm discussing. Just wait for a moment. Right. Now, you see, when we are talking about the disasters, we are knowing that the basically two things are associated with the disaster. One is the loss of life, and another is economic loss. And if you look at this here, if you look at the loss of life, if you look at this chart, then out of 100%, 47. If I say 100% die, 100% die in disasters, then out of 100, 47 die in earthquakes, 45 in cyclones, 7 in flood, and in other disaster, rest of is 1% other disasters, right? So highest contribution is coming from the earthquake, so it is important. Now second part is the economic loss. If you look at the economic loss, if I lose 100 rupees, 35 I'm losing in earthquake, 28 in cyclone, 30 in flood, and 7 in other disasters, right? So again, the maximum economic loss is also observed during the earthquake. So that's why the earthquake in practice is very important, right? Now if you look at these two charts, you find that in case of flood, the loss of life is very less, and the economic loss is very high. What is the reason? The reason is we are able to predict flood most of the time, right? When we are able to predict the flood, we are saying that okay, we are issuing the warning. We are saying people that you go to the safe places, or the places having the high altitude, right? So don't live in the low lying area, right? So we can basically we can have few loss of life during the flood, but at the same time economic loss is very high because our properties get ruined, and because of that economic loss is higher. So what I want to convey is, in future when we are able to predict earthquake, right now we are not able to predict earthquake, and therefore the problem is there, right? If you are able to predict earthquake in future, then loss of life can be reduced, right? So right now we are not able to predict earthquake. It is very difficult. People are working on it, but nobody is successful. Some different theories are coming up, and they are saying that okay, these are the observations we have to keep in mind to predict the earthquake. But I think we need a lot more data, and we don't have that data. So right now we are not able to predict the earthquake, right? Now actually what is happening, the impact of earthquake basically it is affecting everything: life, society, property, civic communities, lifeline, heritage, economy, development. I think everything, right? uh, uh, if you have observed any one earthquake, I tell you, you will not remember it for the lifetime. right? So this uh, loss of life generally we are observing, right? Uh, Now this loss of life is, I think, it is not uh, permitted, right? Loss of life is not allowed at all when we are designing any building. Our building should remain safe under each and every circumstances, right? Our building should remain safe under all sorts of disasters, under all sorts of disasters, right? So I think this is a you can see the destruction of the human life. As a civil engineer, we do not want to see such kind of pictures, right? It will distract you, right? We do not want to see such kind of pictures, right? These are the pictures from 2001 earthquake, and a lot of work we have done as an NCC officer. And I tell you, I brought a dead body of 8-year-old boy, right, from the debris. Now, at that moment, as a civil engineer, we are asking ourselves that who is responsible for this? Who is responsible for this? Right? And generally, you see, our role as a civil engineer is very important, and therefore I always assume that uh, uh, we are actually involved in this wrong practice. It is not actually intentional, it is unintentional, but we are involved in it, right? And therefore the priority should be given that all buildings should remain safe during earthquake, right? So this picture definitely distract you. Township, I think Anjar, Bachao during the 2001 Bhuj earthquake, almost the whole township was lost, loss of property. Right, this is a ground plus four-story building. Now it is of no use, so huge economic loss, and as it is collapsed, there may be a loss of life. Right, you can see such kind of pictures during the earthquake. Right, sometimes a column get damaged. Now here, this column is of no use, I tell you. And even though your building survived, it means your building is lucky, right? Your building is having lot of redundancy, right? And this redundancy plays an important role during this earthquake, right? And here, this building survived. The one of the reason is there may be a reserve strength comes in picture, right? Otherwise, this column cannot take any more load, right? Now, once it is get damaged, you have to retrofit it. So cost is involved, right? So economic loss is always there. You can see the health centers. This is the hospital in Bhuj, which was collapsed during earthquake, right? Now, hospital is the most important building, and we need after the earthquake, right? But as it is collapsed, so we cannot do anything here, right? You can see the schools damaged. Now in Gujarat, the most of the schools are built up with the prefabricated elements, and the joint detailing was very poor before earthquake. I tell you, after earthquake, it was improved because we have learned a lot from this earthquake of 2001. So if you look at this, uh, I think this joint detailing was improved. During Bhuj earthquake, 12,000 schools were damaged or collapsed, I tell you. Right? And most of them are prefabricated, made up with the prefabricated element, and the joint detailing was poor. Heritage structures, they are affected by the earthquake, and I tell you, uh, uh, we are not able to restore it because a lot of workmanship is required, and we don't have those artisans, right, who can rebuild the same thing, right? So heritage is damaged. Once it is damaged, we it is very difficult to restore it, right? Loss of heritage. You can see this is the darwaza. This is the Mani Mandir in the Morbi. It was get damaged after 10, 12 years. It was partially restored. I tell you, partially restored. This is a fort of Bhuj. Uh, it got damaged, and I think it was very difficult to carry out. Lifelines. You can see railway bridges, roads affected a lot. Now, when such kind of damage is taken place, it is very difficult to carry out rescue and relief operations. Right. So this is very difficult. Electric power generally is got damaged during the lifeline, like harbor structures are affected. The harbor structure made up of RCC affected a lot during the Bhuj earthquake. The industrial damage. Generally, the the light shade of industrial structure is generally safe during earthquake, but generally the heavy shades which are made up of the RCC, they absorb the tremendous damage during the earthquake, right? And this economic loss is very difficult to estimate, right? So I tell you, during Bhuj earthquake, almost we have lost 25,000 crore at that time. Now you can say it may be a 2 lakh crore or more than that, if you consider today. Right. So this loss is very difficult to estimate, and I tell you that uh, uh, this the economic loss is quite significant, along with the loss of lives also. So the important thing is what we learn from this earthquake is important. Right? We have to learn something from the earthquakes. If this period is gone, for example, in 2001 earthquake came in Gujarat, and from 2001 to 2008 9, the Bhuj which was the epicenter, right? The whole Kutch district was rebuilt, or rehabilitation was taken place, and it was tremendous. I tell you, right? And this disaster which was happened there, it was converted into an opportunity. Right? It was converted into opportunity, and the whole Kutch region was developed like anything. It is considered, means today if we consider Kutch, it was considered to be the one of the most advanced district in Gujarat. Lot of businesses are coming up, industries are coming up in the Kutch, right? And at that moment, our Prime Minister Narendra Modi was CM here, and because of his vision, I tell you, the development of Kutch was tremendous, and I think the World Bank has taken note of it, and World Bank has appreciated that this is the case that everyone can discuss, where we are saying that the disaster become uh, a blessing for the Kutch region, right? Disaster taken place, but we have learned a lot, and rehabilitation was taken place in a wonderful way. And like Kutch is a district, I think people are visiting nowadays as a tourism spot also, along with the industrial development, right? So if you look at this hazard vulnerability in India, the 54% land is vulnerable to earthquake, 8% land vulnerable to cyclone, and 5% land vulnerable to flood. Right. And if you look at the earthquakes, now we talk about earthquakes, then out of this 54% land, basically, the whole India is divided into seismic zones, and 2, 3, 4, 5, and the 12% land is liable to severe earthquakes, 18% land is liable to intensity of 8, which is Latur Uttarkashi, and 20% land is liable to MSK intensity scale 7, right? This is what the 7 major tectonic plates we have. India is here. I think India is here. You can see this is India, and this India. If you look at the boundary on the northern side and northeast side, right? Now this boundary, the two plates, Eurasian plate and Indo-Australian plates are meeting, right? And because of this, you see this Indo-Australian plate is going below the Eurasian plate, and here we have a Himalaya. So one plate is creating pressure on another plate. So Indo-Australian plate is going below the Eurasian plate, and therefore the height of the Himalayas keep on increasing. We are knowing that like a few crore years back there was a sea, but now there is no sea, and now there is a mountain of Himalayas, right? So this continuous movement is going on. Right now this movement is going on. So one plate is creating pressure on the another plate, and therefore this red line is very critical for us. And this red line will tell you that big earthquakes will come along this line, because these two plates are creating pressure on each other, right? And this is the seismic zone map. You can see this when two plates are meeting, the whole north and northeast part is in zone 4 and 5, right? I think south is very safe, means it's safer than other parts of India, because it is not lying on the boundary of the two plate, right? But the few earthquakes are also coming in the south also, but they are not dangerous. This is the epicenter map, and you can see the most of the earthquakes, 98% earthquakes are coming on the border of the two plates, right? These are the This is the boundary of the two plates, right? And most of the earthquakes are coming on that boundary because these plates are creating pressure on each other. Once they create the pressure on each other, one plate will break and earthquake will come, right? So this is what the global occurrence of the earthquake. We are saying that the great earthquake, we say magnitude 8 and higher, we are expecting one great earthquake every year. Yeah, this is the whole earthquake engineering is based on probability. I'm saying every year we are expecting one great earthquake. It means we are expecting. It may come, it may not come. Right? If it will not come, then next year the probability will increase that there is a probability that a great earthquake may come next year, right? So the whole earthquake engineering is based on probability. So if you look at this, the magnitude is decreased and the number of earthquakes per year is increased, right? It means a big earthquakes, what we can conclude? We can conclude that big earthquakes are rare. Big earthquakes are rare. Small earthquakes are frequent. You can see here the magnitude 8, right? We are expecting 8 and higher. We are expecting one earthquake. And if it is less than 3, how many earthquakes we are expecting every year? This is not every year. You get this 8,000 per day, 8,000 per day. So 9,000 earthquakes we are expecting every day, right? Every day. But these earthquakes are not, I tell you, these earthquakes are not important for us. These earthquakes are not important, right? Because the amount of energy released in these earthquakes are very less and they will not damage our structure. But the important thing is these earthquakes are very important for us. These earthquakes, right? So you can say magnitude more than 6 to 6.9, 120 earthquakes are annually occurring in the world. 7 to 7.9, 18 earthquakes. 8 and higher, it is 1. So 140, these 140 earthquakes are very important, right? And these 140 earthquakes are causing tremendous damage to our structure, right? And these earthquakes are known as moderate earthquakes, moderate, right? And these are the minor earthquakes, right? So we are not worried. So basically, understand, the big earthquakes are rare, small earthquakes are frequent, and moderate earthquakes are occasional. This is what we can conclude from the slide. And our philosophy of earthquake resistant design is the same, right? So it is a three-step philosophy. We are talking about the minor shaking. Minor shaking means having a smaller earthquakes which creates a minor shaking. So a minor shaking taken place, then there is no damage in the structural member. There is a damage in the only non-structural members, right? Which is repairable. But when a moderate shaking is taken place, then non-structural part will damage and the structural part will also get damaged. It's a minor damage. It is repairable. And when the strong shaking, like a Bhuj earthquake, right? Or you can say the Assam earthquake, or you can say Kangra earthquake, or many other earthquakes. Those earthquakes are strong earthquakes. Now, if I talk about a Bhuj earthquake, which is a recent one, 2001, then we are expecting tremendous damage in the non-structural member. At the same time, we are also expecting a tremendous damage in the structural member. You see here, you just look at this. Here, this is the RC frame structure. Now, this is the beam get damaged, right? Generally, we are expecting damage in the beams. So beam get damaged, and this damage is too significant. It is possible that we have to demolish my building after earthquake, but your building should not collapse during earthquake. Remember, this is the bottom line. So what is the philosophy of earthquake resistant design? The philosophy of earthquake resistant design is your building may absorb damage, but it should not collapse during earthquake, right? So damage is allowed, but collapse is not allowed. Remember, as a civil engineer, if somebody is saying that what is the one-line philosophy of earthquake resistant design, you have to say that damage is allowed, collapse is not allowed. No collapse is allowed. If any building is collapsed, it means someone has committed mistake. Who has committed mistake? That is there is a forensic investigation to be taken place, and then we can say who is at the fault. Right. So We are not going into blame game because we are learner. So we have to learn something. So what should we do to make our structure safe, right? So this is what the philosophy is under minor but the frequent shaking. Non-structural member get repairable damage and structural uh, uh, member will not observe any damage. Under moderate but the occasional shaking, there is a heavy damage which is not repairable and structural damage which is repairable, right? And under strong shaking like Bhuj earthquake, which is a rare, right? So very heavy damage to the structural member and non-structural member. But your structure is not going to collapse. Remember, your structure is not going to collapse. This is the bottom line. Remember, your structure should not collapse. That's all. Damage is expected. Damage is basically we are expecting during earthquake, but collapse is not. We are expecting. We are not allowing. Remember. So, if you take 1994 Northridge earthquake or 1995 Kobe earthquake, if you take the 1990 Turkey earthquake or 2001 Bhuj earthquake, right? Whether it's America or Japan, Turkey or India, or any other nation, we have observed a collapses of the building and the infrastructure, right? This is the scenario. The difference is when a developed country is there and who worked a lot in the area of earthquake engineering, then loss of life they are reducing. For example, uh, if I'm talking about the Bhuj earthquake, almost 13,805 people died during earthquake as per the data of government of Gujarat. And same type of earthquake came in USA. Same, it was 7.7 magnitude, and less than 50% die in America. Yeah, this is the difference between the developing country and developed country, right? So I think we are suffering a lot as far as human loss is concerned, right? Advanced countries like America, Japan, New Zealand, they are performing very well during the earthquake, and I tell you, the loss of life is very reduced, right? So in this developed country, but developing country has to think about it, and they have to implement a major earthquake policy in the country, right now. As far as India is concerned, our priority is not the safety of the structure, right? We are not uh, uh, this implementing this earthquake safety criteria with the punitive actions, right? But right now our priority is that everyone should get roti, kapra, and makan, right? So we are talking about these things, but as far as the building is concerned, we are not talking about we are giving the safe building or not, right? So right now we are not going towards the earthquake safe society. We have not started yet, I tell you, right? America has started the earthquake safety program in 1970, and now still it continues. After 50 years, still America is continuing the earthquake safety program. Now you can imagine how much effort to be needed. If India starts today, then it may take 50 years, 100 years to go to the stage of earthquake safety, right? Various structure elements like column, shear walls, bracing systems, MR frames, tubes, generally we are using as a structural member. They are transferring the earthquake forces to the foundation, to the soil, right? Now, I'm just giving the introduction because I have not started my laboratory part, but basically we have to understand the basics of earthquake engineering, and we have to understand the principle of earthquake resistant design, and we have to understand which member carry the forces. Right? Now, if you look at this is the moment resisting. This is a moment resisting frame, right? This is a brace frame. This is the shear walls, right? This is a simple beam column joints. So beam is a frame structure, you can say. This is the office construction in New Zealand. Yeah, this is the beam column construction. Right? There's a frame structure. These are the braced frames. The various braced frames available. Now, bracing is applied to increase the stiffness, right? Because in experiment also we are going to include such things, right? to increase the stiffness, we are introducing shear walls, we are introducing bracings and other elements, right? This is, you can see, this is the bracing provided, right? Bracing provided, you can say this is the bracing, this is the bracing, right? So these bracings are very useful. In case of a steel structure, it is equivalent to shear wall, right? Basically, the purpose of shear wall, purpose of bracing is almost same, right? To increase the stiffness and reduce the deformation of the structure. You can see the shear wall here, right? The shear wall construction is very easy. You see, before 2001, nobody, no structural engineer in Gujarat, I tell you, 80% structural engineers are not designing the shear walls. Most of the time, we also find that the construction of the shear wall is difficult. But I tell you, the construction of the shear wall is not that difficult, right? And nowadays, I think most of the people are going for the shear wall. I think that is a better. I think there is an improvement we have seen in the Gujarat, right? So we are talking about the construction of the shear wall. This is the shear wall construction, and we are going for the dual system where the frame and wall both are combined, right? We have a special structural systems like frame tubes, truss tubes, bundle tubes, shear walls without triggers, and we are not going to discuss this now. We are starting the initial portion is very important, I tell you, where we are trying to understand what is the philosophy, how the damage is taken place. Damage is taken place in the beam first and then column, right? We are talking about the strong column, weak beam philosophy, right? So we should understand that damage in the beam is allowed first prior to column, right? So first we talk about the beam, damage in the beam, then damage in the column, right? Why earthquake lab is required? Basically, earthquake is a random strong ground motion, right? And which is very complex, I tell you, right? Now, when we go for the earthquake analysis, because earthquake is a dynamic load, so you have to carry out the dynamic analysis, right? But sometimes we carry out the static analysis also. When we talk about static analysis, seismic coefficient method is given in the code, because the code is saying that it is not possible for everyone to understand the dynamic response of a building, right? So the code has given a simplified procedure that is known as the seismic coefficient method. Says it is a basically static coefficient also. So where no dynamics is involved, but it depends on the various values. It is Z by 2, I by R, SA by G, right? So we talk about the various parameters, and these values given in the code, basically it is on the higher side. It is on the higher side, right? So it is giving the penalty that if you don't go for the dynamic analysis, then in the static analysis, your components are safe, but they are not economical, right? So when we go for the seismic coefficient method, most of the time, your seismic coefficient method will give you a higher value, right? And when it gives a higher value, definitely the component of your building, which is not optimized then, because you are designing for the higher level of the moments or shears, right, or the structural actions, right? One very simple thing that if you observe the IS 1893, right? If you follow this, I think you can most of the time you are making your structure safe, or you are making a structure good, right? Now the thing is, the problem comes when you see, we are designing our structure for not the maximum force, right? Our philosophy is earthquake resistant design, not the earthquake proof design, right? We are not going for earthquake proof design. Earthquake proof design means what? In earthquake proof design, for example, 100 kilonewton force is coming on your structure, then you apply the factor of safety, right? For the dead load and live load, we are applying a factor of safety 1.5. So actual load coming on the column is 100, but you are designing for 150, right? Actual load on the column is 100, you are designing for 150. So that is the factor of safety we are talking about. So we are designing for the maximum force which is coming on the structure. But as far as earthquake is concerned, we are not designing for the maximum force, I tell you, right? the maximum force which is coming on a structure and our design level forces, there is a huge difference, right? Design level forces are very less, right? So earthquake forces are much larger than the design forces, right? And therefore we are allowing damage, but collapse is not allowed, I tell you. So we are designing our structure in such a way that it remains ductile, because we are knowing the earthquake supplies the energy. Earthquake first release the energy. This energy is traveling in form of waves. Now these waves will shake the foundation of the structure. It means some of the earthquake energy is entering into the structure, and your building has to absorb this energy. That's all, right? So your building has to absorb the energy. So earthquake resistant design is not a strength based design, it is the energy based design. We are designing our structure in such a way that it will absorb the energy which is supplied by the earthquake. So we try to make our structure ductile. Remember, we try to make our structure ductile, right? So ductile is very important. Okay, so ductility is very important for us, and we have to introduce IS 13920, which is revised in 2016, right? So if you look at the philosophy, this is the only philosophy where collapse is not, means this is the only philosophy where damage is allowed, right? This is the only philosophy where damage is allowed. Collapse is not allowed in any philosophy, I tell you. Collapse is not allowed in any philosophy. Here also the collapse during earthquake is not acceptable. When a major earthquake taken place, there is a revision of the code taken place, right? So this is very important. This is a window period we are saying. This is the window period where we can learn something, right? We can learn from our previous mistakes. In 2001, when earthquake comes in Gujarat, everyone becomes actually very disciplined, and they are following the provision of earthquake resistant design very much, right? But you see, nowadays what happened? After almost it is 20 years, people forgot the earthquake, and now the same practice, what we have observed before 2001 earthquake, the same practice we observe right now in Ahmedabad. The same practice is going on. So right now we are also adding the unsafe houses in the present stocks of the building, right? So I think this is a very dangerous situation. Uh, uh, when earthquake came, we have learned a lot, but then after that, after some time, after 14 15 years, we start forgetting the earthquake, and now again we start committing the same type of mistake which what we have done in the earlier stage, right? So laboratory testing, you see, again I'm saying the earthquake resistant design is design and construction practice. Now, earthquake resistant design, we are knowing the damage is expected, collapse is not, right? So basically, when you allow the damage, means your structural element is entering into the non-linear range, right? Damage means always say a permanent deformation is taken place, and permanent deformation means it is a non-linear stage, right? And you see, during earthquake, it is very difficult to predict the behavior of the earthquake, right? And therefore, always we are saying the laboratory testing of the physical model is become very important, right? So if we test something in the laboratory, if we observe the behavior of the structure in the laboratory, then we are able to understand earthquake properly, right? So this laboratory is very important, and for the basically uh, we need a good laboratory in which a shake table we need. So we discuss that part. So shake table is one of the means of laboratory testing as a model, right? So what exactly we need? We need a shake table, we need the models, these two things we need, and then we perform the experiment on this, and we try to conclude something, right? We try to understand. So I tell you, these are the tests we generally we are performing in the laboratory, right? Free vibration test, where initial displacement, initial velocity test we have. Then we perform the force vibration test, resonance test, the variable frequency with the sinusoidal excitation, transient excitation, vibration table, quasi-static loading, pseudo-dynamic test, real-time dynamic hybrid test, and last one is the ambient vibration test. Ambient vibration test. This ambient vibration test, you can have data from any structure, because ambient vibration means a very small vibration. Basically, it is picked up by the sensor. So suppose if you are going in any particular structure and we have placed a sensor, and this sensor, if records what is the effect of your movement in the building, right? If any movement is taken place, then from that movement, our sensor, we can, with the help of our sensor, we can find out the frequency and natural period of the building, right? More test is required, right? So this is an ambient vibration test. Ambient vibration test means it is a very small vibrations, and this is small vibrations are picked up by the sensor, and we analyze the data which is coming from the sensor. Then we can derive the frequency and natural period of the building, right? So as far as what we are going to discuss today is free vibration test, is initial displacement and initial velocity test, and force vibration test means resonance test, variable frequency sinusoidal excitation, and vibration table means shake table test. This we generally focus during this lecture, because we are not able to cover all in 1.5 or 2 hours, right? So basically you need 3 things, right? First, the equipment to provide dynamic force. It means you need the earthquake simulator. It means you need a shake table which provide the earthquake motion, right? So it depends that which type of shake table you have. A shake table which allow the movement in all the 3 direction, or 2 direction, or 1 direction, right? So it depends. So equipment to provide the dynamic force is earthquake simulator. It is not shake table. Second is a model. Models we need because we want to study something. So shake table only shake the top plate, but this model will give you the give you the idea of the behavior of the structure, right? And last is the instrument setup. You see, if you want to analyze the data, you have to put the sensor, and the sensor will sense the movement of the model, and it will capture by the computer, right? And then you analyze those responses of the building, right? So that is to be required, right? And for that you require a sensing unit and a data acquisition system, right, for the data, right? So the shake table. The shake table is a laboratory instrument which is capable of producing the ground motion, right, during earthquake. Actually, this shake table, which type of shake table you have? It's a mechanical, it's maybe a servo hydraulic. Like the shake table, what we have is a mechanical shake table. So when we are talking mechanical shake table, it is very difficult to produce earthquake ground motion, right? But if it will become servo hydraulic, then definitely we can produce the earthquake motion of the earthquake which is taken place in the past, right? वो हम कर सकते हैं. Basically there are 6 degrees of freedom, right? वो 6 तरीके से मूव हो सकता है, X, Y, and Z, and then 3 rotations, right? But we are knowing that so these are the 6 degrees of freedom we have. 6 degrees of freedom, right? So each and every mass can move 6 ways: delta X, delta Y, delta Z, theta X, theta Y, theta Z, right? So this is what you have. So we prepare a prototype or a scale model in the laboratory, and then we test in the laboratory. It will help. Shake table test will help you investigate the problem of the linear and non-linear structures. So shaking table test deals with the non-linear studies. Now you can see these are the earthquake simulator. This simulator is in California, University of California. Right. So this is one of the big shake table we have. It is 20 feet by 20 feet, 20 foot by 20 foot का है, or 1 lakh pound is its capacity. Servo hydraulic actuator. You see, that's why I'm saying this is a servo hydraulic shake table. Servo hydraulic, right? It is not a mechanical shake table. It is horizontally driven by the 8 actuators, vertically by the 4 actuators. Original acceleration up to 1.5, right? Now it has a 6 degrees of freedom. This shake table will move in X direction, Y direction, Z direction. It's same way rotate about the X axis, rotate about the rotate about the Z axis, and then rotate about the Y axis, right? So it is having two translation component, means original direction X and Y, one vertical component, and three rotational component, pitching, rolling, and reviewing. And we right now we are eliminating the rotations. Rotations are small as compared to the translation. This is the earthquake simulator in NID Mica, Japan. This is considered to be world's biggest shake table, right? Biggest shake table. And you can see the loading frame on both the sides. So they start. Uh, uh, they are doing the testing on it, and this is the world's one of the biggest shake table. It is 20 meter by 15 meter, right? 1200 ton load you can apply, right? This is the shake table at IIT Roorkee, right? It is smaller size, but it is very good facility we have. And this is the 1/5 scale model. You see, this is a model. This is not the real structure. It's a 1/5 model of the 7-story RC frame is tested in UC Berkeley, right? So now we are talking about uniaxial shake table, uniaxial, right? Now when we are going about the 6 degree of freedom of the shake table, it become too costly. Now if it become too costly, then nobody will purchase, or few institutes may purchase, right? Who those institutes who have good grants, right? So basically we have 3 rotations and 3 translations. We are not considering rotations, right? Why? What is the reason why we are not considering rotations? Hello, can anybody answer? Hmm? Hmm? Can anyone answer? Why we are neglecting rotations? Hmm? What is the reason? Yes, Wasimji, you can.
Sir, because of loading is directly rotation is not possible in column and beam, so we are neglecting for rotations. There is a failure in axial and flexor also.
Right. Okay. Anyone else, please? The reason is basically, yes, please.
So because earthquake, the waves are move in X direction or Y direction.
Okay. The correct answer is basically the wavelength. If you look at the wavelength of the earthquake wave, is maybe 2.53 kilometers, right? And when we are talking about our structure, the structures maybe most of the time our structures may be a 20 meter or 30 meter in width, right? So as compared to the wavelength of the earthquake wave, our structure is coming at one particular point. So we assume that all the foundations will experience the same earthquake ground motion, right? It is not variable, and therefore what we are assuming that rotation component is not going to come in picture. But when we are talking about the long structure means we are talking about the pipeline. For example, if we talk about the pipeline, then a pipeline is 500 kilometer long. Now when we are talking about the earthquake wavelength, which is 2.5 kilometer, then 2 points of the pipe will observe the different vertical acceleration, right? When it will move like this, there is a possibility of rotation, right? So in case of a long structures, generally we are considering the rotations, but normal structures like buildings, we are only considering the translation component, right? Translation component, right? Is it clear? Okay. So we have 2 original components. So we talk about the 3 translation component. Out of these 3, 2 original component we have, right? 2 original component means we have this is the original component we have, and this is the vertical component we have. right? So X, Y, and Z. And again, now horizontal component and vertical component, we are saying now out of these two components, which one is dangerous? Which one is dangerous? Horizontal or vertical? Which one is dangerous?
Horizontal.
Why horizontal?
So
Why
because
horizontal?
most of the earthquake force is on the horizontal axis, because X and Y is also, this Y is a vertical component and Z and X are a horizontal component. So all
No, that is not the correct answer. Anyone else want to try? You see,
ग्राउंड में शेक्स इन हॉरिजॉन्टल डायरेक्शन नो सर
ground original direction shake, vertical direction में shake होता है. I tell you. You see, have you heard about the fact of 1897 Assam earthquake? उसमें क्या हुआ था? People have seen that the stones which were lying on the ground, which are moving in the upward direction, right? Upward direction is what? When the stones are thrown upward, right? When the stones are moving in the upward direction, it means the vertical acceleration is more than 1g, isn't it? Then and then it can move in the vertical direction. Yes or no?
yes, sir.
So when it moves in the vertical direction, it means the vertical acceleration is quite significant. It is more than 1g, right? So such kind of things we have seen near the epicenter. Right? So near epicenter, the vertical acceleration you cannot neglect. But when you go away from the epicenter, the vertical acceleration is basically coming down. Right? It reduces. And it reduces means, well, there is this component of vertical acceleration reduces after 20 kilometers, right, from the epicenter. So near the epicenter, the vertical component is quite significant. But when you move away from the epicenter, this vertical component is basically reducing drastically. And if I'm saying, if you're talking about the structure which is 100 kilometers away from the epicenter, then most of the time the horizontal component remains significant, right? Vertical component is become almost negligible, right? And therefore we are saying that this is very important. Which component? The horizontal component is very important, right? Because most of the structures are away from the epicenter. Near epicenter, you have to consider vertical acceleration. Remember. Now, the horizontal shake table moment is equivalent to horizontal shaking on the ground, right? Now, we said uniaxial. Why? Why uniaxial? Why not biaxial, triaxial? The triaxial means X, Y, and Z. I said that vertical component is not important. So now only two horizontal component is there, which is important for our structure. And now, you see, if I design a biaxial shake table, it is difficult, right? It is costly also. So if I design a uniaxial shake table, then I can test my model in one direction. Then I change the orientation of the model. Remember, I am changing the orientation of the model, right? If I change the orientation of the model on the shake table, I get the another direction. So I can test my model in both the direction. So we can test in both the horizontal direction, right? So instead of the simulating all the 6 degrees of freedom, which is basically costly, we are going for uniaxial shake table, right? Uniaxial shake table, which is, you see, I'm not talking about the hi-fi research right now, right? My perspective is that we have to understand the basic behavior first of all. So we just want to give the original ground motion, right? Original ground motion, and then we try to understand what is happening to our models, and then we try to connect with the real life structures, right? So generally we have a shake table. This is the 8 feet by 4 feet shake table. This is the another shake table is 5 feet by 4 feet. We have the actually 4 shake tables in the laboratory. This is 2 by 2, a small so small testing we can carry out here. This is the 5 by 3. This is the 8 by 4 feet shake table, right? These shake tables are the different ranges we have. The frequency range is 0 to 25 hertz, right? The payload capacity is 500 kg. It is only 500 kg. It's not higher than, but actually the reserve strength is, we are saying, is more than 1000 kg. 1 ton capacity is there. you can apply the movement, means displacement 2 mm to 60 mm. That is the stroke length. That is the you can apply. Basically, we have placed a shake table. You can see here the shake table is basically on concrete block, right? So this is the machine foundation, right? This is the machine foundation. On the machine foundation, we have placed the shake table, right? This is the instrumentation setup. This is the vibration analyzer. This is 16-channel analyzer. This is a uniaxial accelerometer and the triaxial. This is uniaxial sensor and triaxial sensor, right? Uniaxial means it will measure the acceleration in only one direction, and triaxial it will measure acceleration in all the three directions, right? Now the experimental setup, right? So what we need from the experiment, first of all, you have to determine the property of the model, right? So this is the primary requirement. You have to determine the stiffness of the model, right? So we perform the impact hammer test, free vibration test, and these are the three tests we generally perform on the model, right? But before that, we also perform this test. I tell you, this test means we determine the property of the model and the stiffness of the model, right? So we have prepared a frame like this, right? So what we do here, look at this. Here, these are the brackets, right? These are the steel brackets, and this is the platform. And we are placing our model here, right? And when we are placing the model here, right, the model is like this. And then what we do, we apply the force here. We apply the force here. We are locking. You see, this is locked here, so this cannot move, right? But when we apply the force, what is going to happen? The movement of the one floor is taken place, right? And we can measure. It is like this, right? This is the force we are applying, right, on the first story. And when we apply the first story, the top story will move. There is a rigid body. The deformation is the ground story. So you determine the K1 stiffness of the first story, and then you lock the first story. You are locking, and you are applying load to the second story. So you get the stiffness of the second story, right? So you get K1 and K2. This is the story stiffness you will get actually in the laboratory, right? This is very important. So first, you see, don't assume anything. If you have a model, then test everything in the laboratory. So you have to determine the stiffness also, right? And then we perform the free vibration test. Where we are disturbing the model. When we disturb the model, what happens? It start moving, right? It will start moving, and after some time it will stop, right? So you see, free vibration test means what? Free vibration means only initial disturbance is there. Only initial disturbance, right? We are disturbing the model first, and then it will vibrate on its own elastic property. So this is the acceleration or displacement versus time curve, and initially it is high, and gradually it reduces, right? Gradually it reduces. So this is basically from this point, this peak to this peak, right? This is the natural period T. Right? And this is the amplitude. I tell you, this is what the amplitude is, right? The amplitude is keep on decreasing. You see, amplitude is reducing in each and every cycle because it is a free vibration. We are not applying any external force except the initial disturbance, right? Here you can see it is keep on reducing. It is like this. It is like this. It is reducing all the time, right? So this is the equation where you as it is reducing, you also calculate damping in the system. Yeah, damping is very important. Damping is good for the structure, I tell you. Damping will absorb, if the proper damping is there, it will absorb more energy, right? And our philosophy is saying that you have to absorb the energy. We are not designing our structure for the maximum force. We are designing our structure in such a way that it will absorb the maximum energy. And this is the equation given in the Chopra. And I think we can use this to determine the damping ratio, right? Now, how we perform the test, right? Here I'll show you how we perform the test, right? Just look at this. Free vibration test is very, very simple. In free vibration test, we are just disturbing the model, and we allow the model to vibrate on its own elastic property, right? We are placing the sensor. Look at this setup. This is very important. I'm just showing the video of the testing which is carried out in the laboratory, right? Look at this. This is the model. Right? Look at this. This is the sensor. This is the sensor we have placed on the each and every floor. Right? Now what we do? It is very simple. We are just disturbing the model. This is a very simple frame model, you can say, right? And just we are disturbing. Now it start vibrating, right? And you can see here, this is a computer. It is connected. Sensor is basically connected with the computer. These wires are connected with the vibration analyzer, and this is recorded, right? And you can have a you can see here, you can see the deformations here, right? You can see this, right? So you can get a graph here like this, and in each and every cycle, displacement or amplitude is keep on decreasing because of damping, right? So this is now the free vibration test. So from the free vibration test, what we can determine? We can determine damping ratio, right? Damping ratio we can determine. Then we also determine the frequency of the sample. The second test what we perform is the impact hammer test. Right? So what we do? This is the impact hammer. Impact hammer is having a sensor here, right? This is a sensor, right? Now we are applying the impact in a model, right? It means some energy is applied. When you hit this hammer to the model will vibrate, right? So we can see the impact hammer test. It is also known as the initial velocity test. But again, this is very simple test. Just look at this. This is the model, spring mass model. It is disturbed, right, with the impact hammer. Impact hammer is having a sensor. So how much energy is applied, we are knowing, right? And we have placed a sensor here. यहाँ पे सेंसर है, इसके ऊपर सेंसर है, ये सारे सेंसर्स है. So सेंसर यहाँ पे है. So the sensor will record the vibrations, right? So this is the impact hammer test. The frequency what you get from the impact hammer, frequency what you get in the free vibration, it is same. I tell you, you get the same frequency. Okay. So this is the impact hammer test we are performing to determine damping ratio, and the second part is frequency, right? Then we go for the shake table testing. You see, I'm talking about not the testing which is carried out at of the research level right now, right? So the whole earthquake setup was prepared for the undergraduate student to understand the structural behavior, right? This is what our main aim is. So basically, the whole setup was made up for that, and then the same facility can be used for the research also, I tell you. So at the end, if time permits, I will discuss that part also. But right now, I am discussing from the perspective of the undergraduate students, right? So now the third test is the shake table test. So we have learned the free vibration test, impact hammer test, now the shake table test. So what we do is we put our model on a shake table, and then we apply the shaking at the foundation level, and your model will vibrate. And how it vibrates, we are placing the sensor on the top of the model, and we try to record it. What are the responses, right? So we determine the frequency, acceleration, natural period. This can be determined, right? So I'm talking about a single-story building. This is a single-story building. Single-story building means having only single floor, because we are knowing that very heavy mass. Heavy mass कहाँ पे है इसमें? Where the heavy mass is located? कोई बता सकता है इसमें? Heavy mass कहाँ पे है? Single storage structures में heavy mass कहाँ पे है? At what level?
Roof level.
Am I audible?
Yes, roof level. At roof level.
Am I audible?
Yes, sir, you are audible. Yes, sir.
Hello.
Yes, sir, you are audible.
Hello.
Sir, you are audible.
Hello. Am I audible?
Yes, sir. Yes, sir.
Okay. Sorry. 1 minute. Yeah, I'm audible, right?
Yes, sir.
Yeah. Sorry. So it is at the floor level, right? Maximum, because there is a slab and slab is having a very heavy mass. So a concentrated earthquake force is acting at the floor level, right? Now, if you look at along the height, earthquake force is acting, but it is very small as compared to the force at the slab level. So a concentrated load is acting at the floor level, right? So if you look at the mathematical model, the mathematical model will be like this. This is the structure where the heavy mass is located at the floor level, right? So we prepare a model like this is a spring mass model, and we draw the free body diagram, right? And then we determine the frequency. The frequency is 1/2 pi square root of k by m, right? This is the natural frequency. And what is the value of k? The value of k is here. What we assume is a 12 EI upon L cube, right? 12 EI upon L cube. We assume that mass is not allowed to rotate, right? So 12 EI upon L cube. This is the. So it depends. K depends on what? K depends on what? Support condition, modulus of elasticity, moment of inertia, and the length or height of the element, right? So the frequency depends on what? K and M, right? So simple. If the k increases, then what happened? Frequency will increase. If k reduces, frequency will reduce. If mass increases, frequency will come down. If mass reduces, frequency will go up, right? So you have to correlate this with the stiffness and mass, right? Stiffness and mass, and stiffness depends on many other parameters, right? Many other parameters. So first, the basic model we have developed is a spring mass model we have developed, and basically we want to understand the effect of various parameters. कौन से parameters है? Modulus of elasticity, moment of inertia, height, mass. This is what we want to study, right? उसका effect क्या आता है? So basically the 4 models have been prepared with a different material. Different material means we have changed the E. हमने E change किया यहाँ पे. Height means we have changed the length. हमारा basic equation ये है कि 12 EI upon L cube, right? 12 EI upon L cube. So we are changing parameter one by one, right? Different mass, right? This is K by M. So mass we are studying, and thickness. Thickness means we are studying effect of I, right? BD cube by 12. So we study I also. So we have prepared a 4 model. For example, here you see the mass is same, only the material is changing. So we are studying what is the effect of E on the model, right? Then we take a data, means we perform a test, and then we recorded the response of the model, right? For mild steel, you get a FFT, acceleration versus frequency curve. This is one of the FFT. You get like this, right? For stainless steel, it is the record FFT curve is like this. For flexiply, it is like this, right? Now you can see the behavior, right? So this is very important, right? Spring mass system with a variable material, right? Variable material. Look at this. This is very important. Here you can see, first I apply the low frequency, right? Low frequency. All the models are experiencing the same motion. सबको एक ही motion दिया जा रहा है, लेकिन the first model, the first part is vibrating more as compared to other three, right? Because it is having a low frequency. This is a low frequency. The frequency of shake table is low, so both are matching. So resonance is taken place. Now I am increasing the frequency. मैंने frequency increase किया, right? Now what is happening? पहला वाला उसका response कम हो गया, right? Now the response of the second model is increasing, right? You can see the second model vibrates more as compared to other three. Still I am increasing the frequency, right? मैं अभी उससे ज़्यादा frequency दे रहा हूँ. अभी उससे ज़्यादा लूँगा तो क्या होगा? अभी देखो, the first and second stops. Means उसका vibration कम हो गया. Now the third start vibrating. Look at this. This is called resonance. Resonance means frequency of structure or frequency of the system matches with the external frequency. The large deformations had been observed. Now look at this. This is the resonance, right? In the third model. Then still I am not happy. I am still increasing the frequency. What is happening? Look at right now the third model is vibrating. Now still I am increasing the frequency. What is happening? Look at this. The first three is now not responding to that extent. Now the fourth model start responding, right? The fourth model is start responding, and this is very important, right? So from this experiment you can understand the resonance part. It is very difficult for the student to understand. We are saying that okay, frequency of system matches with the frequency of the shaking, resonance taken place. But you see, when I was studying, I was also confused how it is done. If we are able to see the experiment like this, it is very easy to digest, right? Otherwise, we believe our professors earlier, right? But actually, we are not getting we are not actually convinced, right? We are respecting our professors and we are assuming they are right. But when we are see such kind of experiment, then we can definitely believe in our understanding, right? So what we do here, you see, we are performing the test using the shake table. Then we are modeling the same thing in the STAD also software, and this is the theoretical value, right? This is we have calculated. Now look at this. These are almost on the same range, right? So that also you can compare, right? The second model is variable height. Now here all other parameters are same, all right? There are four. So mass is same. Is a cross section dimension of this vertical strip वो भी same है. उसका फर्क क्या है? उसकी height L का फर्क है, right? Now which part is the stiffest? This is the stiffest, and ये क्या है? ये flexible है. ये एकदम flexible है out of these four, right? And then we perform the test, right? So we get the result like this. Then different mass. You see, everything is same except the mass. Now here, this is having the least mass, और ये mass यहाँ से बढ़ता जा रहा है. The red is having the maximum mass. So किसकी frequency ज़्यादा होगी? The frequency जिसका mass कम होगा उसकी frequency ज़्यादा होगी. जिसका mass ज़्यादा है उसकी frequency कम होगी, right? And we can determine this again, and we can find out, right? I'm not showing the experiment right now because we have to see many more experiments. Spring mass model with the variable thickness. यहाँ पे बाकी सारे parameters same है. The only difference is यहाँ पे उसकी thickness change हो रही है. इसका thickness है 2 mm, 4 mm, 6 mm, 8 mm जैसा thickness है. तो ये thickness change होने से उसका I moment of inertia change होगा. Moment of inertia change होगा तो I बढ़ता जा रहा है तो उसका moment of उसका stiffness भी बढ़ते जाएगा, right? So we get the result. When we talk about the 3-story building, for example, this is a 3-story building. If you look at this, this is the first story, this is the second story, this is the third, right? Third floor slab. The first, second, and third, right? So basically, we have prepared a model, very simple model. You see, the model what we have prepared is basically not a scale model. The model what we have prepared, we have taken a material such a way that you can see the deformations correctly, right? Our idea is to actually look at the deformations, right? Look at this. When I'm I'm taking this model and I'm basically modeling in the software, then I'm getting the first mode, second mode, and third mode. These are the first, second, third modes, right? So this is the modeling in the STED, right? Now, if you look at this, what I did is look at this. Again, experiment, we'll see, and then we try to understand, right? Look at this, right? Now here you can see this story height is quite high, right? And this story height is the first, so ground floor is maximum, first and second story is less. So the height is more, means it is L cube, 12 upon L cube, right? So it will become soft. It becomes soft means उसका stiffness कम हो जाएगा. Stiffness कम होगा तो larger deformation जो ground floor पे आएगा. हम देखते हैं क्या होता है. Look at this. Just see the behavior. मैंने बताया कि हमें देखना है डिफॉर्मेशन. जैसे लार्ज डिफॉर्मेशन देखोगे आप देखोगे तो पता चलेगा कि हमें उसको हमारे एक्चुअल स्ट्रक्चर डिफॉर्मेशन बहुत कम होते हैं. हमको उसके साथ कंपेयर करना है, राइट? नाउ लुक एट दिस. व्हाट आई एम डूइंग, इनिशियली आई एम अप्लाइंग द लो फ्रीक्वेंसी. लो फ्रीक्वेंसी पे क्या होता है, हम ये देखो, ये पूरा मॉडल है वो फर्स्ट मोड में वाइब्रेट कर रहा है. तो फर्स्ट मोड में वाइब्रेट कर रहा है तो तीनों मास एक ही डायरेक्शन में जा रहा है, ठीक है? नाउ मैं फ्रीक्वेंसी बढ़ाता हूं, आई एम इंक्रीजिंग द फ्रीक्वेंसी. मैं फ्रीक्वेंसी बढ़ाता हूं, क्या हुआ, उसका शेप देखो चेंज हो गया, डिफॉर्मेशन शेप. मैंने फ्रीक्वेंसी बढ़ा दिया, उसका डिफॉर्म शेप चेंज हो गया, राइट? इट मे एंटर इनटू सेकंड मोड, थर्ड मोड, राइट? सो ये जो है हम एक्सपेरिमेंट करते हैं तो पता चलता है कि हाँ, ये फिर से मैं आपको बताता हूं. ये मैंने लो फ्रीक्वेंसी अप्लाई किया. जब मैं लो फ्रीक्वेंसी अप्लाई करता हूं तो क्या होता है, it try to vibrate in the first mode because the lowest frequency is known as a fundamental frequency. तो उसमें तीनों मास एक ही तरफ जाते हैं, देखो, है ना? अब मैं फ्रीक्वेंसी बढ़ाया तो उसका चेंज हो गया पैटर्न, राइट? सो इट मे वाइब्रेट इन द सेकंड मोड, थर्ड मोड, राइट? सो हमें वो मोड शेप क्या होता है, मोड शेप स्टडी करने के लिए हमें ये चाहिए, ठीक है? सो लुक एट दिस. नाउ मैं फ्रीक्वेंसी बढ़ाता हूं तो देखो क्या होता है, यू कैन सी दिस, राइट? सो उसका डिफॉर्म शेप भी चेंज हो गया. तो सिंपल चीज हम ये भी बोल सकते हैं बच्चों को कि अगर फ्रीक्वेंसी ऑफ शेकिंग इज नॉट मैचिंग विद द फ्रीक्वेंसी ऑफ योर स्ट्रक्चर, देन आपका स्ट्रक्चर को नुकसान नहीं होगा. अगर मेरे स्ट्रक्चर की फ्रीक्वेंसी लो फ्रीक्वेंसी है और हाई फ्रीक्वेंसी के अर्थ पे गया तो मेरे स्ट्रक्चर को कुछ नहीं होगा, क्योंकि वो मैच ही नहीं हो रहा है ना? तो रिजोनेंस आने की संभावना नहीं है. अर्थ के में जनरली रिजोनेंस नहीं आता है, आई टेल यू, रिजोनेंस नहीं आता है. Now here you can see, ये टेस्ट हमने जब परफॉर्म किया तो आपको यहाँ पे देखो, ये 1 2 3 4 masses are moving on one side, it is vibrating in the first mode. और यहाँ पे देखो दूसरा हमने देखा तो क्या मिला हमें, अभी ये देखो ये सेकंड मोड. तो ये कुछ मासेस, ये मास है कहाँ पे मूव हो रहा है, ये मास इस तरफ मूव हो रहा है, राइट? और ये मास कहाँ पे मूव हो रहा है, ये मास यहाँ पे मूव हो रहा है, राइट? सो you can see the deformed shape. It may be in second mode, third mode. It is right now in the second mode, right? So we determine the frequency in the first, second, third mode. Is the first frequency 2.1, then 6.5 to 11.32, right? Now lowest frequency is known as the fundamental frequency. So ये क्या है? What is this? This is the fundamental frequency, right? ये fundamental frequency है. Now हम स्ट्रक्चर की डिफिशिएंसी की बात करें. हम जनरली ग्राउंड स्टोरी, सॉफ्ट स्टोरी होता है, राइट? ओपन ग्राउंड स्टोरी है या उसको सॉफ्ट स्टोरी बताएंगे, वर्टिकल इरिगेटिव या स्टीफेंस इरिगेटिव में लेता हूं, राइट? नाउ अब देखो क्या होता है. जनरली ग्राउंड फ्लोर किस लिए यूज होता है? ग्राउंड फ्लोर इज यूज फॉर द पार्किंग. ये पार्किंग के लिए यूज होता है, राइट? तो यहाँ पे आपको वॉल नहीं दिखाई देगी, सिर्फ कॉलम है. और ऑन द अपर साइड यू हैव कॉलम, यहाँ पे कॉलम है, यहाँ पे वॉल भी है, राइट? कॉलम एंड वॉल. सो ये अपर पार्ट बहुत स्टीफ हो जाता है और लोअर पार्ट फ्लेक्सिबल होता है, तो उसको क्या बोलते हैं हम, ओपन ग्राउंड स्टोरी और द सॉफ्ट स्टोरी, राइट। ये देखो, ये पार्किंग के लिए हमने अभी भी ये यू सी गुजरात में 2001 अर्थक्वेक में अहमदाबाद में करीबन 128 बिल्डिंग 128 बिल्डिंग्स वर कोलैप्स्ड इन अहमदाबाद. They are ground plus 4 story, and 95% buildings are like this. 95% where parking at the ground story is given, and from the people are living from the first story, right? So this ground story becomes soft. This is the soft story, right? Open ground story is a soft story, and the most of the deformation is focused on the ground story, right? Look at this. This is the open ground story, right? Look at this. These are the pictures of open ground story or the soft story structures, right? After earthquake, most of the people are stop this practice, right? And nowadays again the same type of mistakes we are committing in Ahmedabad. We have learned, but we have now forgotten everything, and the wrong practice started in Ahmedabad, right? Look at this. This is a ground plus 5-story building, right? Now this is basically a open ground story, right? The larger deformation is focused on the ground story. So what is happening? If you look at this, the most of the deformation is on the ground story, right? The upper part, it behaves as a rigid body. ये पूरा rigid body के टाइप में behave करेगा. So पूरा एक unit की तरफ वो move होगा. So कैसा होगा? It is behave like an inverted pendulum. ये inverted pendulum की तरह behave करेगा, right? So ये जो हमारा pendulum का जो आर्म है वो, और यहाँ पे heavy mass, ये पूरा mass ये इसको represent करता है. So the whole, it is like an inverted pendulum and it is vibrating, right? So what is happening? What is the effect? You can see here. Tremendous damage, right? You can see this is the soft story. The ground story is collapsed, right? Upper story is, I think, intact. Nothing has happened. But because the ground story collapsed, the whole structure collapsed. Look at this. People are saying that the whole building sink in the ground. It is not sinking. Ground floor columns were collapsed. It's a soft story, and soft story failure is observed. So you can see the first floor will become ground floor, right? So it is in Kutch 2001. You can see this. This is again a soft story, right? Here a glass partition is provided, right? Glass partition, because you have a beautiful view of mountains here, right? So you want a glass partition, so you can say, okay, I can sit in the garden and see this. So I want a glass panel. But when you put a glass panel, it becomes soft and become soft story, open ground story, and because stiffness of the glass is very less as compared to the wall. So upper part is safe, ground story columns collapse. This is a soft story failure, which is observed 1971 San Fernando earthquake, right? You can see this is the same type of the failure, right? Soft story failure. So what we do, first we try to study what is the soft story effect, right? हम वो थोड़ा एक्सपेरिमेंट के तौर पे देखते हैं, ठीक है? तो आपको पता चलेगा कि सॉफ्ट स्टोरी क्या होता है. सॉफ्ट स्टोरी में मैक्सिमम डिफॉर्मेशन कहाँ पे आता है? ग्राउंड स्टोरी पे, राइट? रिमेंबर, ग्राउंड स्टोरी पे डिफॉर्मेशन आएगा. Just wait for a moment. These all are my students of civil engineering. They are performing the experiment. Look at this. Here, what we did in the same model, we on the ground story only columns are there. On the first story, column plus these are the steel walls. Walls are there. So it is ground story becomes soft and upper story is stiff. Now what happened with C? What dekhte hain? So you can appreciate. Just look at this. If you look at this, the most of the deformations are on the ground story. Look at this. So, and my students are very conservative. they are not applying good ground motion. They feel that it will break, but if it collapses, I think we get a better idea. Now you can see this behavior. This is very important, right? This is actually the soft story behavior, right? Again, I'm saying, you look at this. Look at this. From this, you can see. Right? Look at this. Total deformation on the ground story. Upper portion remains rigid, right? This is very important, right? Fine. Now we go for the failure, soft story failure. We can see जब भी कोई स्ट्रक्चर फेल होता है तो बहुत मतलब दुख होता है इन रियल सेंस, बट जब लेबोरेटरी में वो फेल होता है तो उसको देख के हमें आनंद भी होता है कि भी या वी हैव लर्नड अ लॉट, राइट? वी कैन सी हियर द सॉफ्ट स्टोरी फेलियर. Again, I have to change it. एंड आपको ये देखना है कि ये जो स्टूडेंट है वो एक्सपेरिमेंट जो देख रहे हैं उसका फेस भी आपको देखना है साथ में, राइट? जो ये फेलियर जो इसका बिहेवियर देखती है तो उसमें क्या इंपैक्ट आता है. जस्ट लुक एट दिस, राइट? ये भी सॉफ्ट स्टोरी है. ऊपर शियर वॉल है, यहाँ पे ऊपर शियर वॉल है, ग्राउंड फ्लोर पे शियर वॉल नहीं है, तो इट इज फ्लेक्सिबल हियर, इट इज स्टीफ हियर, राइट? नाउ लुक एट दिस. क्या होता है आप देखो, ये लेवल ट्यूब है, वो देखता है कि फ्लोर लेवल पे है कि नहीं. अब देखो ये डिफॉर्मेशन बढ़ता गया. ग्राउंड स्टोरी का कॉलम में डिफॉर्मेशन बहुत ज्यादा आ रहा है ना, बहुत ज्यादा आ रहा है. सो द लार्जर डिफॉर्मेशन ऑन द ग्राउंड स्टोरी. एंड लुक एट दिस नाउ, क्या हो रहा है. जस्ट लुक एट दिस. ये शेकिंग कंटिन्यूज है, ये कंटिन्यू हो रहा है. एंड देन look at this and it is gone. Yeah, it is gone. Look at this, it is gone. है ना? यही चीज हमारे रियल स्ट्रक्चर में होती है, right? The larger deformation. Now look at the smile on the face. Now this is the learning experience, right? And you if you touch it, वहां पे आप टच करोगे तो ट्रूमेंडस, मतलब बहुत गर्म होगा वो, बहुत मतलब ये इतना वाइब्रेशन होने के बाद वहां पे ये हीटिंग भी होता है, right? So you can see this. So a lot of energy has been absorbed. वहां पे absorb की गई, लेकिन it is not sufficient, I tell you. तो इसलिए वो बाकी की एनर्जी नहीं absorb कर पाया, it fails, right? So this is very important for the students to learn like this, right? So this is a soft story failure, right? Then sometimes soft story जो होता है, ये सारे रीडिंग्स है. आई एम नॉट डिस्कसिंग द रीडिंग्स राइट नाउ. आई एम जस्ट टॉकिंग अबाउट द क्वालिटेटिव बिहेवियर, राइट? ये पूरा डिस्कस करने में ये सिर्फ ओनली डेटा नहीं है, उसके पास काफी कुछ डेटा हम थियोरेटिकली, प्रैक्टिकली एंड सॉफ्टवेयर में चेक करते हैं, राइट? नाउ अवॉइड द सॉफ्ट स्टोरी ऑन अपर स्टोरीज आल्सो, राइट? कई बार ये सॉफ्ट स्टोरी नीचे नहीं ऊपर भी बनता है. कई बार कोई बंदा बोलता है कि मुझे 5th फ्लोर पे मुझे ऑडिटोरियम चाहिए, तो it may become soft. Look at this. ये जो है पोर्शन है, it becomes soft हुआ तो larger deformation ये collapse हुआ, right? ये अर्थक्वेक को सिर्फ 2 मिनट लगता है, नेचर को सिर्फ 2 मिनट लगता है उसको उसकी डिफिशिएंसी फाइंड करने में, राइट? 2 मिनट अर्थक्वेक 2 मिनट चलता है, 2 मिनट में वो सारी डिफिशिएंसी फाइंड कर देता है. दैट इज द पावर ऑफ नेचर, आई टेल यू. डोंट चैलेंज द नेचर एट एनी मोमेंट, राइट? लुक एट दिस. ये जो है इंटरमीडिएट सॉफ्ट स्टोरी, राइट? कोलैप्स हुआ. आई एम टॉकिंग अबाउट एसिमेट्रिक शियर वॉल. कई बार ऐसा होता है कि द आर्किटेक्ट इज सेइंग दैट ओके you cannot put shear wall in the front because I want a good appearance. तो अब अगर आप फ्रंट में नहीं shear wall प्रोवाइड करते हो तो क्या होगा, आप पीछे प्रोवाइड करोगे तो अनसिमेट्रिकल हो गया. अब अनसिमेट्रिकल हो गया तो क्या होगा वो हम देखते हैं, राइट? अभी क्या हो रहा है ये देखिए. Now look at this, right? हमने एक तरफ shear wall रखा है, दूसरी तरफ shear wall नहीं रखा है, तो क्या होता है देखो बिल्डिंग में. तो एक स्टीफ हो गया, दूसरा फ्लेक्सिबल हो तो उसमें टॉर्शन आ गया, ये सारे कॉलम में टॉर्शन आ रहा है, राइट। आपके आपके फ्लोर्स रोटेट हो रहे हैं, आपका ये भाग है वो ज्यादा मूव हो रहा है, ये पार्ट कम मूव हो रहा है। अगर शेकिंग होगा तो यहाँ पे ये पूरा फ्लोर जो है आपका स्लैब है वो रोटेट हो रहा है, वो रोटेशन की वजह से कॉलम में क्या आता है, द कॉलम कम्स अंडर टॉर्शन। सो द टॉर्शन जो है वो हमें जनरली एलिमिनेट करना होता है, बिकॉज यू सी इट इज वेरी डिफिकल्ट टू हैंडल अर्थक्वेक फोर्स। अगर अर्थक्वेक में आप उसमें टॉर्शन भी डाल दो तो आपकी लाइफ और मिजरेबल हो जाएगी, isn't it? Your life will become more miserable if you introduce torsion in your structure, right? And therefore I'm always saying that go for the simple and symmetrical structure, avoid torsion, right? अगर torsion आपने input कर दिया तो your life become very miserable as a structural engineer, right? ये सारे सेंसर्स के रीडिंग्स है, मतलब क्या डेटा कैप्चरिंग। देन वी हैव a model like pounding, when the दो स्ट्रक्चर एक दूसरे के करीब होते हैं तब वो एक दूसरे को हिट भी करते हैं, राइट। तो वी विल सी कि क्या होता है ना, ये दो स्ट्रक्चर है वो एक दूसरे के करीब है, राइट। दोनों की फ्रीक्वेंसी अलग अलग है ना। जो शेकिंग हो तो जो अर्थक्वेक की फ्रीक्वेंसी तो दोनों के लिए सेम है, लेकिन दोनों की शेकिंग फ्रीक्वेंसी अलग अलग है, राइट। सो व्हाट विल हैपन, हो सकता है कि ये जो स्लैब है वो कॉलम को हिट करे, राइट। हमने उसको अर्थक्वेक के लिए तो डिजाइन किया है, लेकिन ये इंपैक्ट के लिए हमने डिजाइन नहीं किया है, वी हैवंट डिजाइन इट फॉर द इंपैक्ट। तो क्या होगा, हमने डिजाइन नहीं किया है कॉलम को तो ये कॉलम फेल हो जाएगी, राइट। एंड डैमेज मतलब कोलैप्स हो सकता है या डैमेज हो सकता है। ये स्लैब टू कॉलम है, कई बार कॉलम स्लैब टू स्लैब भी कोलिजन होता है, राइट। अब हियर यू कैन सी यहाँ पे दो बिल्डिंग एक दूसरे से, देखो ये यहाँ पे आई थिंक यू गेट अ बेटर व्यू, दिस बिल्डिंग कोलैप्स्ड, राइट। जब भी दो बिल्डिंग नजदीक हो तो एज अ स्ट्रक्चर इंजीनियर क्या करना चाहिए, हमारा बिल्डिंग स्ट्रांग होना चाहिए, दैट्स ऑल, तभी हमारा बिल्डिंग बचेगा। अदरवाइज ये तो लाइटर मोड पे है, लेकिन हमें ऐसा डिजाइन करना है कि वो एक दूसरे को हिट ही ना करे, राइट। अगर हिट करता है तो वो देखिए दे आर एबल टू एब्सॉर्ब द इम्पैक्ट लोड, राइट। लुक एट दिस, राइट, एट द टॉप the collision is taken, this is a pounding taken place and this is collapsed because it is a weaker, this portion is weaker, right. Look at this, the same thing has happened here, right. Here also you can see a damage has been taken place after pounding. Look at this, right. So we have prepared a very simple model. This is just again for the undergraduate students, right, not for the research work. Again, I'm saying just behavior part we want to understand, right. The very simple model has been prepared. Like sometimes you have a slab to slab collision, right. Sometimes you have a slab to column collision, right. These are the two models, right. So we see pounding of slab to column. Slab column को कैसे हिट करता है ये देखते हैं हम। अब देखो कि ये दोनों बिल्डिंग है, एक है 2 स्टोरी, दिस इज अ सिंगल स्टोरी बिल्डिंग ना, दोनों की फ्रीक्वेंसी अलग अलग है। हम उसको दोनों को सेम मोशन तो एक ही दे रहे हैं, तो व्हाट हैपेंस, लाइक मोशन इज सेम, फ्रीक्वेंसी दोनों की अलग है, तो दोनों कैसे वाइब्रेट होते हैं देखो। अभी जस्ट लुक एट द सिंगल स्टोरी बिल्डिंग एट द लो फ्रीक्वेंसी इज वाइब्रेटिंग, फ्रीक्वेंसी उसकी कम है, राइट। अभी मैं फ्रीक्वेंसी थोड़ी बढ़ाता हूं तो ये दूसरा मॉडल भी वाइब्रेट होने लगा। अब नाउ दे आर हिटिंग ईच अदर, दोनों एक दूसरे को कॉलम के ऊपर हिट करते हैं, दोनों के स्लैब, राइट। एंड वी आर नॉट डिजाइन, हमने उसको डिजाइन नहीं किया है बेसिकली उसको इंपैक्ट के लिए, तो वो फेल हो जाएगा। वो सिंपल थिंग, दिस इज नॉट द पाउंडिंग ऑफ द स्ट्रक्चर, राइट। लुक एट द पाउंडिंग ऑफ द स्ट्रक्चर, है ना। सो लुक एट दिस, yes, this is the pounding, it is hitting the column, right. Slab is hitting the column, right. And pounding of slab to slab, sometimes दोनों slab एक ही लेवल पे होता है, slab to slab pounding होता है ना। तो वो भी देखते हैं। लुक एट दिस नाउ, नाउ हियर दोनों एक ही लेवल पे है, राइट। और जब वो हिट करते हैं तो इतना ज्यादा इम्पैक्ट आता है, आई टेल यू। हम जब लेबोरेटरी में टेस्टिंग करते हैं तभी भी इतनी ज्यादा आवाज आती है। इन रियल सेंस जब रियल स्लैब्स टकराते होंगे तब कैसा होता होगा, राइट। जस्ट लुक एट both the slabs are hitting each other, right? So basically this impact is supposed to transfer to the column, but this slab to column is worst as compared to slab to slab pounding, right? Slab to column is the worst, right? Look at this, very simple, है ना? So I think we'll get it, right? So these are the actually readings we are taking exercise time, and then we are finding out what is the frequency of the model, what are the displacement, everything we find out, right? ये देखो मैक्सिमम फोर्स, इतना ज्यादा फोर्स उसमें आ रहा है, 34.6 26.7 है, इतना ज्यादा फोर्स। और यहाँ पे देखो ये जो है ना, ये जो आपको स्पाइक दिख रहा है, यहाँ पे जो स्पाइक दिख रहा है ना, वो सारे इम्पैक्ट है। यहाँ पे इम्पैक्ट होने से वहां पे ज्यादा एक्सेलरेशन आता है, राइट। ये जो है स्पाइक, दैट इज द बेसिकली द पाउंडिंग, राइट। नाउ ये पाउंडिंग आने से यहाँ पे एडिशनल फोर्सेस जनरेट होते हैं, राइट। सो उसका रेमेडी क्या है, आपको दोनों के बीच गैप रखना है। और गैप हमें सोचना है कि दोनों बिल्डिंग एक दूसरे की तरफ जाएंगे, ऑपोजिट डायरेक्शन में मूव होंगे, राइट। वो ऑपोजिट डायरेक्शन में मूव होने के बाद हमें क्या करना है, हमें देखना है कि एक दोनों का मूवमेंट क्या है। तो हमें पता है कि मैक्सिमम ड्रिफ्ट एज पर द कोड इज 0.004h, तो उसको मल्टीप्लाई बाय r करोगे तो दैट इज द मैक्सिमम एक्सपेक्टेड लेटरल डिस्प्लेसमेंट। तो एटलीस्ट उतना आपको दोनों के बीच डिस्टेंस रखना है, राइट। सो यहाँ पे क्या होना चाहिए कि उतना रिमेडियस तो सेम है कि दोनों के बीच सिर्फ आप जगह रखो, दैट्स ऑल। गैप आपको डिजाइन करना है, ये गैप डिजाइन करोगे तो पाउंडिंग नहीं होगा। कई बार हम बोलते हैं एल शेप बिल्डिंग, सी शेप बिल्डिंग, एस शेप बिल्डिंग नहीं अच्छे हैं। यहाँ पे एक्चुअली ऐसे बिल्डिंग जो थे सी शेप के बिल्डिंग यहाँ कॉलेप्स हुए थे अहमदाबाद में, राइट। तो क्यों कॉलेप्स होते हैं, राइट। यू कैन सी दिस इज द सी शेप बिल्डिंग, राइट। तो सी शेप बिल्डिंग का प्रॉब्लम क्या है, उसका मोमेंट ऑफ इनर्शिया इज डिफरेंट इन बोथ द डायरेक्शन, राइट। तो उसका वाइब्रेशन भी अलग अलग होगा। तो जो जहाँ पे कनेक्ट होता है सी शेप में, जहाँ पे कनेक्ट हो रहा है वहां पे ज्यादा फोर्सेज आते हैं। ये देखो, तो ये जो है ऐसा बिल्डिंग में अगर दोनों कनेक्ट है तो यहाँ पे ये कॉर्नर पे बहुत ज्यादा फोर्स आएगा, राइट। यहाँ पे वहां पे डिफरेंशियल मूवमेंट आता है। ये कॉर्नर है तो इसको बोलते हैं री एंट्रेंट कॉर्नर, यहाँ पे इसको बोलते हैं री एंट्रेंट कॉर्नर। तो वहां पे ज्यादा डिफॉर्मेशंस आएंगे। ये देखो, ये सारे बिल्डिंग इतना अच्छा परफॉर्म नहीं करेंगे अगर हम उसको प्रॉपरली डिजाइन ना करें तो, राइट। ये जो बिल्डिंग गिरा था, मैंने आपको बताया था शिखर टावर, अहमदाबाद में ग्राउंड प्लस 10 स्टोरी के 2 बिल्डिंग गिरे थे, उसमें से एक शिखर टावर, वो भी एक्चुअली सी शेप का बिल्डिंग था, राइट। ये सी शेप के बिल्डिंग देखो, राइट। तो क्या होता है, कई बार आर्किटेक्ट बताता है कि भाई आप आगे शेवल नहीं रखोगे, आपका स्टेयरकेस पीछे ले जाना है, यू वांट टू टेक योर स्टेयरकेस ऑन द बैक साइड। हम पीछे रखेंगे तो क्या होगा, ये पोर्शन स्टिफ हो गया, ये पोर्शन फ्लेक्सिबल है। अभी ये ज्यादा मूव होगा, ये कम मूव होगा, तो इसमें टॉर्शन आएगा। तो हमें अर्थक्वेक फोर्स को डील कर रहे हैं, टॉर्शन को भी हमें देखना पड़ेगा। और हमारा, मैंने बताया ना कि टॉर्शन आता है तो वो बहुत गंभीर बाबत है, राइट। इट इज वेरी सीरियस मैटर एज फार एज टॉर्शन कम्स इन पिक्चर। इफ टॉर्शन किस में आता है, कॉलम में। स्लैब का रोटेशन होता है, कॉलम में टॉर्शन आता है, राइट। तो देखो ये पूरा बिल्डिंग में टॉर्शन आ रहा है और दे परफॉर्म्स वेरी पुअरली ड्यूरिंग अर्थक्वेक। ये देखिए आप, ये देखिए, राइट। these are the reasons. So हमने जो टेस्टिंग किया वो उसको सेपरेट करके किया और दोनों को साथ में भी किया, राइट। ये सिंपल मॉडल, तो उसमें हमने एक कनेक्टर लगा दिया था। ये जो है ना, यहाँ पे ये कनेक्टर है, उसको मैं कनेक्ट कर दूंगा तो इट बिहेव्स एज ए एल शेप बिल्डिंग। यहाँ पे मैंने कनेक्ट कर दिया तो एल शेप हो जाएगी। मैं इसको खोल दूंगा, इफ आई ओपन अप दिस कनेक्टर देन इट इंडिविजुअल, राइट? सो आप देखिए क्या क्या होता है इसमें, जस्ट लुक एट दिस. अभी अभी देखिए क्या होता है. अभी देखो दोनों कनेक्ट किया हुआ है. अभी ये पोर्शन है और ये पोर्शन है, तो ये दोनों की फ्रीक्वेंसी अलग अलग है दोनों, ये ऑरेंज वाले और व्हाइट वाला का. तो हम तो सेम फ्रीक्वेंसी अप्लाई कर रहे हैं दोनों के फाउंडेशन पे, राइट? अब देखो ये टॉर्शन आ गया, टॉर्शन कम्स इन पिक्चर. अगर आप ये कनेक्टर को छोड़ दोगे तो दोनों इंडिविजुअली मूव होंगे, देयर इज नो प्रॉब्लम एट ऑल, राइट? सो वी हैव टू एलिमिनेट टॉर्शन. तो उसको वहां से क्या करना है, उसको वहां से उसको गैप, मतलब वहां पे हमें दोनों को अलग करना है. अलग करोगे तो सेपरेटली बिहेव करेंगे. और ये टॉर्शन, इसमें क्या होता है, एक बिल्डिंग की कारण दूसरे बिल्डिंग में नुकसान होता है, राइट? सो दिस इज बेसिकली अ टॉर्शन, राइट? और टॉर्शन में क्या होता है कि यू गेट द एक्सेलरेशन इन बोथ द डायरेक्शन, राइट? एक्स एंड वाई दोनों डायरेक्शन में आपको दोनों हॉरिजॉन्टल डायरेक्शन आपको एक्सेलरेशन मिलेगा, राइट? लिक्विफेक्शन हमने लिक्विफेक्शन का मॉडल भी किया है, लेकिन आई थिंक मैं अभी डिस्कस नहीं करूंगा. लेकिन उसमें आइसोलेटेड फुटिंग, राफ्ट फुटिंग एंड पाइल फाउंडेशन, ये तीनों का पर स्टडी किया था. और राफ्ट फाउंडेशन जो है वो परफॉर्म बेटर, उसका सेटलमेंट इवन होता है. आइसोलेटेड में डिफरेंस सेटलमेंट होता है ना? तो वो डिस्कस बाद में करेंगे. नाउ डिफिशिएंसी इन द डिटेलिंग ऑफ रिइंफोर्समेंट, राइट? ये एक एक्सपेरिमेंट था जिसमें हमने डक्टाइल डिटेलिंग के हिसाब से पूरा मॉडल बनाया था, और हमने समझाया था कि कहाँ अर्थक्वेक पॉइंट ऑफ व्यू कहाँ रिइंफोर्समेंट की जरूरत है. तो आप देखो ये जो है, हमें पता है कि मैक्सिमम मोमेंट यहाँ पे और यहाँ पे आता है, राइट? अर्थक्वेक में यहाँ पे नुकसान होने की संभावना है, यहाँ पे नुकसान होने की संभावना है, राइट? अब देखो ये नुकसान कहाँ पे हो रहा है, वहीं पे हो रहा है, राइट? ये देखो कहाँ पे हो रहा है नुकसान, वहीं पे हो रहा है, राइट? ऑन द टॉप एंड बॉटम. टॉप में यार बॉटम में हुआ तो हिंजेस फॉर्म हो गए, राइट? लुक एट दिस, राइट? यहाँ पे ये क्यों होता है? कोड ने बताया कि ये आपको वहां पे क्लोज स्टीरअप्स देना है, या क्लोज स्टीरअप्स है नहीं, राइट? तो डक्टाइल डिटेलिंग में बोला है कि नॉर्मल डिटेलिंग अगर डेड लोड के डिजाइन करते हो तो आपका स्टीरअप का स्पेसिंग सेम रहेगा, चलेगा. लेकिन अर्थक्वेक के लिए वहां पे मैक्सिमम मोमेंट आता है, तो वहां पे आपको क्लोज स्टीरअप चाहिए, है ना? ये देखो failures, you can see maximum shear you get here, maximum moment you get here, right? You can see here. You can see this, right? So these all are failure because of the poor detailing, right? यहाँ पे close stirrups नहीं है. टॉप पोर्शन में कोड ने बोला क्लोज स्टीरअप्स चाहिए, लेकिन नहीं है क्लोज स्टीरअप्स, तो उसी की वजह से ये फेल हो रहा है. लुक एट दिस, ये तो जॉइंट फेलियर है. दिस इज द जॉइंट फेलियर, राइट? दिस इज यू कैन सी अ ट्रेमेंडस फेलियर वी हैव सीन ड्यूरिंग जॉइंट का फेलियर, राइट? तो ये जो स्टीरअप्स है वो हमें क्लोजली स्पेस्ड होना चाहिए. ये इक्वली स्पेस नहीं है. सबसे जो कम मोमेंट बीच में आता है तो वहां पे आप ज्यादा स्टीरअप का स्पेसिंग में चलेगा, लेकिन टॉप एंड बॉटम में ड्यू टू अर्थक्वेक मैक्सिमम मोमेंट आता है, तो वहां पे क्लोज स्टीरअप चाहिए हमें, राइट? दिस आर द क्लोज स्टीरअप्स. सो वी नीड अ कन्फाइनिंग रिइंफोर्समेंट हियर, वी नीड अ कन्फाइनिंग रिइंफोर्समेंट हियर. यहाँ पे हम 50% बार यहाँ पे एक जगह कटेल करेंगे, 50% बार दूसरी जगह कटेल करेंगे. सो 50% यहाँ पे, 50% यहाँ पे, राइट? लॉन्जिट्यूडनल बार्स, उसका एंकरिंग अच्छा होना चाहिए, बीम का रिइंफोर्समेंट अच्छी तरह से आना चाहिए, राइट? और ये जो बीम कॉलम जॉइंट है वहां में भी क्लोज स्टीरअप्स होने चाहिए. सो दैट इज टू बी रिक्वायर्ड. सो दिस इज अ डक्टाइल डिटेलिंग, राइट? यू विल अंडरस्टैंड दिस पॉइंट. जब हम फाउंडेशन की बात करते हैं तो यहाँ पे भी आपको कन्फाइनिंग रिइंफोर्समेंट, मुझे पता है कि ये पोर्शन बहुत प्रॉब्लम आ रहा है, तो वहां से हम स्पेशल कन्फाइनिंग reinforcement प्रोवाइड करते हैं, राइट, बिकॉज मैक्सिमम मूवमेंट इज सपोज टू कम. सो डक्टाइल डिटेलिंग है 13 2016 के हिसाब से कन्फाइनमेंट, एंकर लेंथ, बीम कॉलम, जॉइंट डिटेल्स ऑफ सीएस डिटेल्स, लैपिंग ऑफ द बार्स, ये सारे हमने एक मॉडल बनाया था. ये मॉडल है, ये मॉडल में आप पूरा देख सकते हो. ये डॉक्टर एस के जैन है, IIT गांधीनगर के डायरेक्टर. उन्होंने मतलब काफी सारा रिव्यू किया था. हम उनका बहुत सारा आदर करते हैं और उसका गाइडेंस हम लेते हैं. उन्होंने काफी हमें हेल्प किया. This person from the Japan, actually they have seen this. हमने ये जो पूरा सेटअप है वो इंटरनेशनल कॉन्फ्रेंस में डिस्प्ले किया था, राइट. तो मोस्ट ऑफ देम हैव अप्रिशिएटेड कि ये समझने में बहुत इजी है. अंडर ग्रेजुएट स्टूडेंट को समझने के लिए ये बहुत सिंपल हो जाता है. हम कॉम्प्लिकेटेड स्टडी काफी कुछ कर सकते हैं, लेकिन वो जो पेनिट्रेट होना है, बिहेवियर समझना है, तो सिंपल भाषा में समझाना चाहिए हमें, राइट. तो ये सिंपल भाषा में एक समझाने का प्रयत्न हमारा था. You can see this is the ductile detailing. जो रेड पोर्शन है वो उसमें you have to be very careful, right. तो ये जो हमने बताया कि यहाँ पे क्लोज स्टीरअप्स है, ये देखो यहाँ पे क्लोज स्टीरअप्स है, ये जॉइंट का डिटेलिंग है, ऊपर भी क्लोज स्टीरअप्स है, यहाँ पे क्लोज स्टीरअप्स है, यहाँ पे 50% बार ओवरलैप हुए, यहाँ पे 50% बार ओवरलैप हुए, राइट. तो ये सारी चीज समझने की जरूरत है, राइट. तो हमने एक सादा मॉडल बनाया था कि जो मॉडल सिंपल है कि IS 456 का डिटेलिंग वाला और दूसरा था IS 13920. उसमें दोनों में फर्क क्या है वो हमने समझाने का प्रयत्न किया था, राइट. तो इसमें बेसिकली हमारा पर्पस यही था कि बिहेव द सिंपल स्ट्रक्चरल कॉन्फ़िगरेशन कैन बी अंडरस्टूड इजीली बाय दीज एक्सपेरिमेंट्स. द रिजल्ट्स ऑफ एक्सपेरिमेंट्स आर वेरीफाइड by the software, and actual boundary condition can be derived by comparing the NRD and so this is what we have for today, and I think I tried to complete within a stipulated time period. ये जो है हमने उसमें काफी सारे रेफरेंसेस हमने यूज किए थे. ये रेफरेंसेस है. Mean my special thanks to my guide Dr. Ajay Patil. We work closely with the Gujarat State Disaster Management Authority and Gujarat Council of Science and Technology. उन्होंने बहुत मदद किया. हमारे प्रिंसिपल अमन पटेल, उन्होंने काफी हमें फ्री हैंड दे रखा था. जिगर राणा who is my PG student, ध्यान, मजर, मौलिक, other PG students, उन्होंने बहुत सारा काम किया यहाँ पे. श्री अशोक पंचाल एंड श्री प्रफुल्ल पंचाल who is good in fabrication. हमने शेक टेबल जो बनाया पूरा ये एग्जीक्यूट किया. उसे जो शेक टेबल मॉडल बनाने थे ये इन लोगों ने बनाए थे, वो हमारे फैब्रिकेटर थे. उन्होंने काफी बढ़िया काम किया, राइट. तो बहुत बढ़िया काम एज ए टीम वर्क हमारा हुआ था, एंड आई थैंक ऑल ऑफ देम. Here you can see our laboratory is basically visited by Dr. CVR Murthy, Dr. DC Rai of IIT Kanpur, right. So ये सारे लोग हमारे विजिट करके गए थे. ये हमारा जो इंटरनेशनल कॉन्फ्रेंस था उसमें मोदी साहब ने भी ये पूरा का पूरा हमारा जो प्रोजेक्ट था उसको रिव्यू किया था. It was an international conference held at in 2011, right. Here you can see Dr. Murthy and the other dignitaries are there. He is Dr. Marshall from the Peru. उन्होंने उनको भी बहुत मजा आया था. ये बहुत सिंपल है समझने में ये सारी चीज. और ये जो पूरा सेटअप है ना हमने जो बनाया वो इतना चीपर था कि विद इन 5 lakhs हम पूरा शेक टेबल एंड मॉडल बनाते थे 5 lakhs के अंदर. तो गुजरात में करीबन सभी कॉलेजों ने ये सेटअप डेवलप किया है. सभी कॉलेज में आपको ये सेटअप आपको दिखेगा क्योंकि इट इज वेरी चीप, राइट. हमारा उद्देश्य ये नहीं था कि इसमें से कोई प्रॉफिट ले, लेकिन हमारा उद्देश्य ये था कि अर्थक्वेक इंजीनियरिंग पेनेट्रेट हो. और उसी की वजह से हमने कॉस्टिंग इतना कम रखा था कि सभी कॉलेजेस में ये पूरा सेटअप पहुंच गया. एंड आई थिंक स्टूडेंट्स आर बेनिफिटेड फ्रॉम आउट ऑफ इट. दिस ऑल आर एक्चुअली demonstrated during that, and actually Dr. Marshall, Dr. Svetlana Brzev, Marjorie Green, they have visited the earthquake lab. हमारी जो लैब है बनाई है उसमें भी उन्होंने विजिट करके काफी सारा मार्गदर्शन हमें दिया है. So thank you very much for your patient hearing, and now Actually, I am opening the discussion. If you have any question, you can ask, please.
Any
I am
questions
stop
from
presenting.
the any questions from the participants?
Actually, मैंने 2 घंटे में खत्म करने का प्रयत्न किया है,
Yes.
and I hope कि आपको थोड़ा मजा आया होगा, right? So in a very simple language, I try to.
Yes, sir. Yes, sir. It was very excellent presentation, and like in live demonstration, live sessions, you have shown the concept of working of shake table, which was very nicely explained.
Yeah, thank you, ma'am. Thank you. Yeah.
Any questions from the participants? Please, you can type in the chat box also. Any questions?
एक क्वेश्चन ऐसा आया था कि हाउ विल यू कंसीडर द स्लैब स्टिफनेस, ये क्वेश्चन है.
Yes, sir. How will you consider the slab stiffness
yes
during
तो
the shake table test?
या एक बहुत सिंपल चीज है. आपने कभी ये देखा है कि जब अर्थक्वेक आता है तो सिर्फ एक स्लैब कोलैप्स होकर पड़ता गिरता है और बाकी सारा स्ट्रक्चर खड़ा रहता है, बीम कॉलम ऐसे खड़े रहते हैं, ऐसे आपने कभी देखा है? आपने ऐसे कभी नहीं देखा होगा, राइट? क्या होता है, जो स्लैब ये हॉरिजॉन्टल मेंबर है, राइट? ये हॉरिजॉन्टल मेंबर है. उसके ऊपर जब अर्थक्वेक फोर्स आता है, अर्थक्वेक फोर्स कैसा आता है? हॉरिजॉन्टल डायरेक्शन में, राइट? तो ये स्लैब का स्टिफनेस इतना ज्यादा हो जाता है, इतना ज्यादा होता है कि स्लैब बिहेव्स एज अ रिजिड डायाफ्राम. अगर वो रिजिड डायाफ्राम बिहेव करेगा तो उसमें कोई डिफॉर्मेशन बहुत कम आते हैं नॉर्मल सर्कमस्टेंसेस में. अगर आपका स्लैब बहुत लंबा है, इट इज टू लॉन्ग, इन दैट केस हो सकता है कि योर डायाफ्राम बिहेव्स लाइक ए, और योर स्लैब बिहेव्स लाइक ए फ्लेक्सिबल डायाफ्राम. तो उस टाइम हमें स्टिफनेस दिखाने की जरूरत पड़ती है. लेकिन इन नॉर्मल सर्कमस्टेंसेस आपका स्लैब का स्टिफनेस इतना ज्यादा है कि इट बिहेव्स एज अ रिजिड डायाफ्राम और उसमें डिफॉर्मेशन नहीं आता है. इसलिए मैं हमेशा बोलता हूं, आई एम सेइंग दैट द ओनली स्ट्रक्चरल एलिमेंट हु इज एंजॉयिंग अर्थक्वेक इज स्लैब, राइट? उसमें कुछ स्ट्रेस आता ही नहीं है. ये स्लैब की वजह से बाकी सारे स्ट्रक्चरल एलिमेंट में स्ट्रेस आते हैं, राइट? वो स्लैब एंजॉय करता है अर्थक्वेक को, एक ही स्ट्रक्चरल एलिमेंट वो एंजॉय करता है. बाकी जो सारा स्ट्रेस आता है वो बीम और कॉलम के ऊपर आता है, राइट? या तो बीम डैमेज होगा या तो कॉलम डैमेज होगा, लेकिन स्लैब जनरली आपको डैमेज नहीं दिखेगा. स्लैब में क्या होता है, अगर ये स्लैब मेरा है, स्लैब के ऊपर डेड लोड और लाइव लोड आता है तो ये आपका जो स्लैब है वो बेंड होगा. सो स्लैब इज नॉट कंफर्टेबल अंडर डेड लोड एंड लाइव लोड, आई टेल यू. तो उसमें डिफॉर्मेशन आता है. स्लैब में आपको डिटीरिएशन भी आप देखेंगे ड्यूरिंग डेड लोड एंड लाइव लोड. लेकिन अर्थक्वेक में तो स्लैब सिंपली वाइब्रेट ही होता है, दैट्स ऑल, नथिंग एल्स. उसके ऊपर कोई डिफॉर्मेशन आता ही नहीं है. So slab is under stressful condition during dead load and live load, not during the earthquake, right? This is what the general conclusion I am saying. Some कोई typical case हो सकता है कि जिसमें स्लैब बहुत लंबा हो तो उसमें वो फ्लेक्सिबल बन जाता है, तो उसका स्टिफनेस हमें निकालना पड़ेगा, that is different. But under normal circumstances, slab behaves as a rigid diaphragm, right? तो जनरली उसमें स्ट्रेस नहीं आता है. वो स्ट्रेस कहाँ पे ट्रांसफर होता है? या तो बीम या तो कॉलम में ट्रांसफर होता है, राइट?
Yes. So there is one more question that damping ratio experiment of building, which will be helpful for my somebody is asking related to his PhD work.
Yes, absolutely. You see, हमने जो काम किया था, जैसे हमारा जो पूरा सपोज मॉडल देखो तो वो इट इज मेड अप ऑफ स्टील, राइट? और जनरली हम क्या करते हैं कि वी अज्यूम द डैम्पिंग इन द स्टील स्ट्रक्चर इज 2%, राइट? लेकिन हम जब एक्सपेरिमेंट करते हैं तो इट इज नॉट कमिंग टू 2%, इट कम्स आउट टू बी 1.7%, 1.8%, इट इज नियर टू दैट, राइट? सो 20% का करेक्शन आता है हमें, राइट? हमारे एक्सपेरिमेंट के हिसाब से. सो आई थिंक इन योर डिसर्टेशन डेफिनेटली डैम्पिंग रेशियो विल प्ले इंपॉर्टेंट रोल. एंड अभी कभी भी कोई आपको जरूरत पड़े तो यू कैन कॉन्टेक्ट अस ऑल्सो. वी ट्राई टू आपको मदद करने की कोशिश करेंगे, ठीक है ना?
Yes, sir. One more question is there. Any experiment done for multi-support excitations?
एक्चुअली हमने नहीं किया है मल्टी एक्साइटेशन का, क्योंकि उसमें बेसिकली हमें चाहिए लॉन्ग स्ट्रक्चर चाहिए था, और हमारा शेक टेबल का लिमिटेशंस जो है उसी के हिसाब से, मॉडल्स के हिसाब से हमने नहीं कर पाए थे, तो वो हमने नहीं किया है. Any more question? You can share my contact details, madam.
Yes, sir.
And I think if they contact me, I don't mind.
Yes,
Right?
sir. I will share your
Yeah.
mail ID.
Yes, sir.
Yes,
Sure,
sir.
ma'am. Sure, ma'am.
Yes, sir.
Yeah.
Any other questions, please? Can we conduct shake table test for precast construction?
Yes, yes. We can. You see, when we talk about the precast constructions, उसमें क्या होता है? The most important part is the joint detailing, right? मैंने आपको बताया कि गुजरात में जब अर्थक्वेक आया था 2001 में, तो ऑलमोस्ट 11,500 और 600 स्कूल्स वर गेट डैमेज्ड. वो सारी जो स्कूल्स थे, वो सारे स्कूल्स जो थे प्रीफैब्रिकेटेड एलिमेंट से बना था. तो उसमें जॉइंट डिटेलिंग वाज वेरी पुअर, एंड बिकॉज दिस जॉइंट डिटेलिंग, वो जॉइंट्स फेल हुए थे, नहीं कि स्ट्रक्चरल एलिमेंट फेल हुए थे. तो आई थिंक ये पूरा टेस्ट जो है हम यहाँ पे कर सकते हैं. हमने वो किया भी है प्रीकास्ट का, तो वो you can do it, right? Absolutely.
Sir, while going the experiment, what kind of support is considered?
Yeah,
While doing the experiment.
basically you need first of all model. आपको जो मॉडल बनाना है, वो मॉडल आप जब बनाते हो उसका थियोरेटिकल एनालिसिस पूरा हो जाना चाहिए. उसका आपको फिजिकल प्रॉपर्टी पता होना चाहिए. यू नो द फिजिकल प्रॉपर्टी ऑफ द मॉडल फर्स्ट ऑफ ऑल, विच इज वेरी इंपॉर्टेंट. तो थियोरेटिकली आपको वो आपको बहुत फर्म रहना कि ये थियोरेटिकली ये तो है ही है, इसका ये फिजिकल प्रॉपर्टी, इसका मॉड्यूलर वेलोसिटी ये है, उसका आई ये है, उसके ऊपर से इसका स्टिफनेस ये है, ये सारा आपको पता होना चाहिए बिफोर यू परफॉर्म द एक्सपेरिमेंट. देन यू परफॉर्म द एक्सपेरिमेंट. तो उसमें आपको मॉडल जो चाहिए, ये मॉडल के बाद आपको चाहिए इंस्ट्रूमेंटेशन, आपको चाहिए सेंसर, आपको चाहिए डेटा एक्विजिशन सिस्टम, डेटा एक्वायर करने के लिए. तो ये आपको चाहिए. और जब जो सेंसर होंगे तो आपको जो वैल्यू मिलेगा, वो वैल्यू विल बी इन नंबर्स. तो आपको ये नंबर को क्वांटिफाई कर पाएंगे. मुझे पता है कि ये बिल्डिंग एक्सेलरेशन कितना, उसको 1G एक्सेलरेशन ले पाएगा, 1G एक्सेलरेशन. यस, तो 1G एक्सेलरेशन क्या होता है वो आपको पता चलेगा. ठीक है ना? तो सेंसर चाहिए आपको, मतलब इंस्ट्रूमेंटेशन चाहिए, मॉडल चाहिए एंड शेक टेबल चाहिए. दैट्स ऑल.
Sir, what about one question from my side? What about the data acquisition system? Like you are doing in LabVIEW or?
या लैब में मैंने आपको
LabVIEW
यस
with
बेसिकली
software.
नहीं, उसमें क्या होता है कि डेटा एक्विजिशन सिस्टम वो अलग अलग कंपनी का आता है. जैसे हमारे पास जो है वो ओरोस कंपनी का है. ओरोस इज ए फ्रेंच कंपनी. तो उसका जो हमारे पास जो है वो 16 चैनल का है, और उसमें हमारे पास 6 यूनिएक्सल सेंसर है और 3 ट्राइएक्सल सेंसर है. तो ये सेंसर इतने सारे मतलब सेंसिटिव है कि इट विल कैप्चर ईच एंड एवरी मूवमेंट, राइट? तो ये जो सेंसर है उसमें बेसिकली वी आर इंटरेस्टेड इन द एक्सेलरेशन, उसका वेलोसिटी और डिस्प्लेसमेंट हमें इंटरेस्ट रहता है एज ए सिविल इंजीनियर. तो बेसिकली हमें जो मिलता है वो एक्सेलरेशन वर्सेस टाइम का ग्राफ मिलता है, और उसको हम इंटीग्रेट करके वी गेट द वेलोसिटी वर्सेस टाइम एंड डिस्प्लेसमेंट वर्सेस टाइम का कर्व हम फाइंड करते हैं, और देन वी फाइंड आउट ओके एक्चुअल डिफॉर्मेशन क्या हुआ, उसका कर्व जनरेट करते हैं. राइट? या तो
So there is one question. Can we go for welding of bar? Is it effective for the ductility?
यू सी जनरली वेल्डिंग जब बोलते हैं तब हम बोलते हैं कि थोड़ा वो ब्रिटल हो जाता है. तो वो सही है कि ब्रिटल, वो पोर्शन ब्रिटल हो जाएगा. तो यू हैव टू बी वेरी केयरफुल व्हेन यू यूज द वेल्डिंग ऑफ द बार, बिकॉज डक्टिलिटी का तो असर होगा क्योंकि वो थोड़ा ब्रिटल हो जाता है. राइट? लेकिन उसकी जगह जो कपलर्स आते हैं, वो कपलर्स इफ यू यूज कपलर्स, तो आई थिंक अभी कई जगह कपलर्स का यूज होता है. तो कपलर्स विल बी अ बेटर ऑप्शन वो लैपिंग के लिए, राइट, रादर देन वेल्डिंग अ बार.
There is one more question, sir. How to do scaling of models?
ये बहुत बढ़िया.
Guidelines for scaling of model and loading on models.
यस, ये जो है ना, ये सबसे बढ़िया सवाल ये है. ये पूरे हमारा यहाँ पे एक भी मॉडल, इट इज नॉट अ स्केल मॉडल, वो एक भी स्केल मॉडल नहीं है. ये हमने जो किया था वो सिर्फ उसका बिहेवियर समझने के लिए ये किया था. दूसरा पोर्शन है जिसमें हम स्केलिंग भी करते हैं. तो स्केलिंग में बेसिकली यू हैव टू टेक अ पैरामीटर. मुझे पता है कि ये जो है उसको मुझे वेट है या तो स्टिफनेस, वो स्केल मॉडल और द रियल मॉडल को मुझे मैच करना है. तो उसको मुझे स्केल डाउन करना पड़ेगा. उसके लिए काफी सारा मतलब you have to refer a book which is on the scaling of the model, and actually वो scaling of model के ऊपर आप thesis भी कर सकते हो, I tell you, क्योंकि you have to take various parameters, आप वो parameters को one by one scale down करते रहेंगे and you can study it, right? So I think scaling is inevitable when you want to study a behavior of a real life structure in laboratory, right? अगर मुझे ऐसा है कि मेरा आरसीसी का स्ट्रक्चर है, उसको मुझे स्टडी करना है लैब में, तो मुझे उसको स्केल डाउन करना पड़ेगा और तभी मैं कंपेयर कर पाऊंगा दोनों को, अदरवाइज आई कैन नॉट कंपेयर हियर। हमने क्या किया था कि हमने ऐसा किया था कि डिफॉर्मेशन इतना ज्यादा हो कि लोग देख सके, तो डिफॉर्मेशन को अप्रिशिएट कर सके, इसलिए हमने उसके ऊपर कंट्रोल नहीं रखा था। लेकिन इन रियल स्ट्रक्चर्स डिफॉर्मेशन बहुत कम होते हैं, तो वो जो है स्केलिंग विल बिकम वेरी इंपॉर्टेंट। अगर आपको एक्चुअली रिसर्च करना है ऑन अ रियल स्ट्रक्चर्स, तो उसको स्केल डाउन करना पड़ेगा। और वो स्केलिंग के लिए मतलब आई कैन शेयर फ्यू बुक्स ऑन इट, वो बुक्स आपके साथ मैं शेयर कर दूंगा। तो यू हैव टू टेक अ रेफरेंस ऑफ दिस, एंड पैरामीटर कैसे स्केल डाउन करते हैं वो हमें देखना है। जैसे ऐसा है कि उसकी हाइट 9 सपोज 3 मीटर है, तो हाफ स्केल करके हम 1.5 मीटर कर देते हैं, लेकिन 1.5 हम ऐसे नहीं कर सकते। हम मॉडल 1.5 मीटर का कर दिया, इट डजंट मीन कि मैंने उसका 1/2 स्केलिंग कर दिया, ऐसा नहीं है। हमें प्रॉपर्टी देखना पड़ेगा कि उसका स्टिफनेस क्या है, स्टिफनेस के ऊपर क्या इफेक्ट पड़ा, हमने उसका लेंथ 1.5 कर दिया तो काफी सारे चीज होता है। तो आई थिंक उसके लिए हम वो डिस्कस थोड़ा कर लेंगे। आई विल शेयर द बुक्स फॉर द स्केलिंग, राइट?
Yes, sir. Yes,
Yes,
sir.
yes,
Thank you, sir.
Yeah.
Any other questions? Yes, sir. Thank you very much, sir. I think so there are no questions. Thank you very much, sir, for sparing your valuable time, and hope your guidance in future also.
Sure, ma'am.
Yes, sir.
Yeah. Thank you very much for giving me opportunity to deliver lecture here, and I think I have enjoyed. I hope participants have enjoyed also. Thank you.
Yes, sir. Thank you very much, sir.
Yeah.
Thank you.
Should I leave now?
Yes, sir. Yes, sir. Thank you very much, sir.
Thank you.
All the participants,
Thank you, sir.
tomorrow's session will start at 10 a.m. So please join the session and mark your attendance.